Well, hello everybody, and welcome to SkyTour Livestream for this evening, January 21st, 2023. Only 7 more years to 2030. Okay, so tonight, I figured we'll spend some time looking through at some of the fainter objects that we know about in the Orion region, and maybe spend some more time, well, just enjoying this evening. This right here, this one thing that you're seeing right in front of me right now, what you see right there on the screen, that is none other than Betelgeuse. It's the brightest star in Orion, ostensibly, although it is a variable star, so it dims and brightens. Rigel is brighter than Betelgeuse at times. Interesting how that works, but Betelgeuse is a supergiant, a red supergiant in the final stages of life. That means it's in the a branch of its evolution where the next step is probably expected to be supernova. This is a 1 second shot, by the way. We're not stacking this. This is just a live shot of it. So if it goes supernova right now, you'll just see it go really bright on the screen. We could make this a Betelgeuse watch, but that'd be kind of boring, you know, if nothing happens, right? Yeah. Yep. I'm not sure because we don't really understand Wolf-Rayet stars very well. We know of different types. Okay, there are some that expel their hydrogen envelopes, or some that do different things. But you know, when we see the explosive nature of a Wolf-Rayet star, it blows off that outer layer, its envelope. You know, because what ends up happening in stars this big, is their core is down in the center, right? And the outer envelope of material is pushed away from that core. You literally end up with an outer envelope that is separated from the core. And so in a Wolf-Rayet star, the process continues where that outer envelope just goes right off the star and makes this beautiful nebula, like in the Crescent Nebula, like in Thor's helmet. Okay, and these nebulae that are the result can also look just like planetary nebulae, right? In some ways, but I think they're possibly related phenomena. The white dwarf in the middle of the Dumbbell Nebula, for instance, is a white dwarf that is, well, certainly a stellar remnant that's in electron degeneracy. But what's left at the core of a Wolf-Rayet star, right? It could be something different. It could be a neutron star, perhaps. So that's something we don't expect with a planetary. But could it be a white dwarf? Maybe. Depends on the mass of the star. And we don't expect Wolf-Rayet stars to exist below a certain amount of solar masses. And right now, let me tell you, the jury's out on what these stars, how these stars power themselves and what they do in their evolution. Not everybody knows. I want to say hi to Bonnie, who was here first. Nice to see you, Bonnie. Daisy and Zoe are here, and they have Lane with them. Hiya, Lane. So I hope you're watching. This is a good night. And then we have Judy M with us as well. We have Renee Cruz. Hi there, Renee. And I want to thank all of you for coming. Donald Kunzer's with us. Izabela, hello there. How are you? And we have, of course, this Daryl guy. Keeps putting stuff in the chat. I don't know who you are. And Uberku's here with us as well. It's nice to see you, Uberku. And it's an early it's an early night, you know, so it's early in the evening, I should say. Bullwinkle's with us. Mary Kaczynski's with us. How are you? And I think that's about it. I don't see any other new faces yet, but I'm the night is young. Michael Hedrick's with us. He's here. Good to see you, man. And Robin Curtis is with us. Hello, Robin. Nice to see you as well. So we are looking at Betelgeuse at the moment, and I'm just waiting for the evening twilight to end out there and go into full darkness, because when we take pictures of the night sky when it's at sunset, we get a red tinge to our imagery. But let's go in here and take a look at our all sky cam. Let me just take away the Betelgeuse there. Come here, you. All right. Those are the lights of Phoenix out there, 65 miles away. And here you can see the winter Milky Way. I have to clean the dome of the camera when I get out there, or when they go out to do maintenance, they will. So let's just grab another one. You'll see that this is Orion right here. You can see it. Okay, Betelgeuse is right there. That's what we're looking at. And you'll see this move a little bit to this side now as we as we take this new exposure. I took it about 15 minutes ago or so. All right, so watch carefully and you'll watch it move. There you go. Orion is up now. You can see there's Betelgeuse. There is Bellatrix. There is Alnitak, Alnilam, and Mintaka, the 3 belt stars. And then Orion's sword is right here. This is the Orion Nebula. And down here is Saiph, and over here is Rigel. There's an object next to Rigel that I'd like to try and capture tonight. It's called the Witch's Head. I'd like to do that. There are the Pleiades straight up over our head right there, along with Mars right there, and Aldebaran and the Hyades right there, the V shape. And then we have Jupiter down here. We have Capella right here with Auriga, constellation of Auriga right there. So it's actually a very nice evening, okay? And of course, this bird poop is right in the way of the W of Cassiopeia at the moment. Because they can. Yeah. Well, so that's the look of where we are, and Betelgeuse is sitting right there, and we have the telescope aimed over at it. You can see the angle right there of the telescope. And let's see. Hey, Tim F is with us. Hey, Tim. Yep, I said hi to Robin earlier. That's all right. Yeah, so okay, so let's see. Let's bring our computer back here. All right, so what I'll do now is let's go into our planetarium program and bring Betelgeuse back into view here. We have at the angle we're sitting, I bet you we can actually see the Orion Nebula now. We can try it. It's just a beautiful nebula to check out. Might as well do that first while we're here. Alright, so there we go. And looks like we may get it. And we did. It's interesting, you know. It seems effortless, right? That we just say, okay, go to the Orion Nebula, boom, it's in there. You know? And I'm 2,500 miles from this telescope, but we can get everything in there. We had to actually put some redundancies in here in case we lost our place. Daryl remembers what happens before we had these redundant features in place. We would have to hunt for something we knew and then set the coordinates. Remember that? And it was like M4 next to Antares, so we tried to find every night when we got lost. And now that it's no longer an issue, we can just set the coordinates by telling it to search for where it is in the sky based on the star patterns, and that's really nice. Yeah. until we can find our way. That's right. All right, well, let's do this. Let's take a photo. I'm going to do a 15-second photo of the Orion Nebula. I'll tell you why, because I want to show you the extent of the colors, all right? And then we'll go into looking at some details in the background. All right, so we're going to get rid of that, get rid of that. I did a focus, that's why those stars were there. Okay, so there's the Orion Nebula, and that's just raw without processing. There it's processed a little bit, and we can actually draw back that black level to kind of show us a little more detail back out there. Oh, look at that. Yeah, that's nice. So there's the Orion Nebula. So the colors we're looking at are these. Now, the red color, that is ionized hydrogen. Okay. The bluish green, that's ionized oxygen. And that's doubly ionized, and that's O3, Roman numeral 3. Now, the reason that those numbers are like one ahead when I say doubly ionized means 2, but why is it the number 3? Because for every atom, the ground state where there's no ionization is Roman numeral 1. So O1, the regular oxygen atom. O2, Roman numeral 2, singly ionized. And O3 is doubly ionized. The same thing with the other atoms as well. All right. Oh shit.
Testing.
All right, try that.
Well, they say still nothing, huh? I had the mute on my little dongle on my headset was made. They say still no sound.
Okay.
Okay, now they, yes, okay, now they do. I guess that was just a lag right there.
Okay.
Testing, 1, 2, 3, testing. Hello, everybody.
There you are.
Sorry about that.
Interesting. Well, so anyway, I guess I should say welcome, Daryl, because that's the first time that they actually hear me greeting you now, where you actually can respond. So, that's good. So yeah, this is Orion's colors, and you can see this. Now, when I was talking to Daryl before about finding stuff in the sky before we actually had the redundant features to help locate our telescope in the sky, he had mentioned that he remembers where we would just hunt through Sagittarius and we found all kinds of dark nebulae that we didn't know what they were at that point.
Well,
yeah.
Well, we followed the edge of the Milky Way all the way up to Cygnus, and
yeah,
we were finding all sorts of cool dark stuff there along the dark lane of the galaxy, the Great Rift and stuff.
Oh yeah, quite amazing. It was an amazing journey, and we still do that from time to time, and it's fun to do that right here in Orion. All right. Now the thing that I want to mention to you guys too is this. Here, the Orion Nebula. Look at the detail in here. It's stunning, right? And this nebula deserves a little wider view. So let's pull it over, and let's drop down our stacking process. Now you get the full view. Now, what's neat here is you get to see all these rich colors that are in the nebula, and they are indeed there. They're really there. But when you look at this in the telescope, the greenish parts, which are these parts here, the greenish blue parts, these are the ones that you'll see more readily as potentially green. And the reason is because your eye is the most sensitive to green. It's an evolutionary the manner by which our eyes evolved. So looking at this this screen here, you can see that you'd probably see green in these outer fringe areas here. These are pretty bright. And the center part, you might see green in here as well, because if we were to drop this down just a little bit, I'll give you an idea of what you'd see. So let's drop this down. Okay, you see how that's kind of green? Okay, that's the sensor on the camera reacting to the overabundance of green ionized, doubly ionized oxygen in the middle of the nebula. All right, and the stars in the middle of the nebula are called the trapezium. And these actually are 4 hot stars, among others, that help light up this nebula. But it's a beautiful location. And then right up here is the Running Man Nebula. Now, at first it looks like it's separate from Orion, and we've talked about this before. It's separate from the Orion Nebula, but it's really not. Okay, it's actually behind a dark rift of cloud right here, and this dust, because again the universe is in 3D. So if we were to bring this in and bring up our white level, or mid level rather, now you can see at least a little bit. You can see this cloud here that's blocking what's behind it. Okay, and that is in fact the problem, the reason why we see what look like 2 nebulas here, but they're not. There's actually one nebulous region right here, but it's being blocked. Now, this whole region is called the Orion Molecular Cloud Complex, OMCC. And the OMCC is a place where you have lots and lots of dark nebula. And this dark nebula is my hot button, as we've talked about so many times. The dark nebula is the place where the fundamental chemistry of the universe is located. It is the location where all the supernova remnants have dispersed their material into, in part, and it's made up of silicon. It's made of little specks of iron atoms. It's made up of calcium and carbon and magnesium atoms, phosphorus. It's all there because it was made in the hearts of a star, and in the hearts of many stars, and then dispersed to the interstellar medium once it became free of the star by a supernova, and because of a supernova. So looking at this dust here, it's very clear that this is where it's at. This is where life comes from, right? And when you look at the Orion region, you also notice that it's everywhere in this region. So the Orion Nebula has been likened to be like a blister of activity on the edge of the Orion Molecular Cloud Complex. And that's kind of what we're noticing, isn't it? So now what I'll do is I'm gonna move us down. All right, we've stacked 28 of these. That's a lot, but I'll stop it right there and save this. Let me name it though. We'll call it the Orion Complex. Well, I guess I should actually have my fingers on the right keys. Otherwise, it's the Zipflafipidifida. Okay. Orion Complex.
Careful, you could invoke Cthulhu or somebody.
I know, right?
I'm not careful.
I know. Let's bring our telescope back here for a minute. All right. Okay, so the Orion Complex is there, and I'm going to bring back our stack. I'm going to redock it at the bottom here. There we go. And so let me process this in a way that gives us a little bit more of a proper looking nebula region. This is just beautiful.
Would you like that Orion deep exposure just to show people?
What?
Would you like that Orion deep exposure I have to show people where we are and where we'll be going tonight?
Yeah, sure. Throw that in the chat.
Okay. Just a second.
All right, so what we're going to do now, guys, is now that I've let this go a little longer, this is 28 frames, and this is only a 15-second exposure. All right, so I'm going to save this, all right, as a 15-second exposure. And there it's saved, and I'll save it exactly as seen. All right, there we go. All right, now I'm going to clear this and go back to a 1-second night vision mode. All right, so here we are.
Okay, there it is. Whenever you want it.
Okay, thank you.
Sure. Now my Skype went away.
Did?
Not completely. If you can still hear me, I just don't see it now.
Yeah. All right, let's see here. All right, there we go.
There it is.
So this is the region we're looking at. Okay. This is the horse head right here. Okay. And this is Betelgeuse right here. This is Bellatrix. We have Alnatok, Alnalam, and Mintaka. And then we have Scythe, and we have Rigel. And this is what's called Barnard's Loop. It's the remnant of an old supernova that happened somewhere in this region. And it's right around there, perhaps, if you draw a logical center, radius from the center. But it could have drifted. There's the Orion Nebula. And we're going to be exploring this region right here. All right, so we'll be exploring that. Lots and lots and lots of detail in this region. I mean, lots of detail. So we're going to come back now and come back to that. All right. Okay. So now what we'll do is we're going to head down south. So we're going to move the camera south, drop the telescope down, and we'll have it right near the top. Okay.
Say we may try the witch's head tonight.
Yes, I'm going to try the witch's head tonight.
All right, cool.
It's probably available now, actually. But we'll see.
Okay.
Okay, so I'm going to drop it. Actually, this is good right here. And this little guy right here is an object that you'll see. It's actually called the 13th Pearl, or the Rubber Stamp Nebula. It's also known as NGC 1999, I believe. And it's an area where there's a reflection nebula that has a black void, which might actually be a void. Might actually be a void. So, we're going to check that out too. So let's back out a little. There you go. That's too far. All right. So now what we'll do is move just a little bit south some more. Actually, just a bit. Okay, we'll get our guider back in play. And then we'll do another exposure of 45 seconds down here. All right, we are guiding, and I'll wait till we stabilize. There we go.
Temperature compensation on?
I haven't turned it on yet.
Okay.
I probably should. I mean, I could right now. I mean, and we're good. We're at 8.25 Celsius out there. All right, so let's bring up our live stack and clear this past one and get rid of our... All right.
would be about 46, 47 degrees Fahrenheit.
Yeah. Okay, so let's do this. And right off the bat, you can start to see this amazing cloudiness that's here. Let's color correct that. All right, and then pull this back a little bit and pull this over with it. And then come in here. All right, so there you can see that that's going to present itself. Very nice. And look at the 13th pearl, this little guy here. This is an area here, okay, where you're going to see a lot of nebulous detail. It's really interesting, okay? And so, again, we're focusing on this area right here. Right? We're going to be looking here, here, and of course there. All right? So let's, we can zoom in on that in a minute here. All right, so let's go in there. You can see the blue reflection nebula right here.
Mm-hmm.
You can see some very, very subtle strands of nebulous detail. And they'll just become more and more clear as we let them stack. There's only 3 stacked right now.
Are you okay? Cat got your tongue?
I'm waiting.
Oh.
Yeah. You always tell me I talk too much, so I give there to be time. I let time pass sometimes so that you can talk if you want to.
What a guy.
I know, right? Hey, Greg O'Brien, good to see you.
Hi, Cindy.
And Cindy Murphy's here. Hey, that's cool. Nice to see you. Cosmic Ray is with us. Ray says, when are we going to go to Cygnus? He complains that I always go to Cygnus.
Yeah.
That's okay.
Cygnus is just barely still up, but...
yeah, it's way in the northwest.
Yeah. It's probably actually setting right now.
Yeah. Indeed. Okay. Well, you can see this is looking good now. Let's move this out a little bit. And change this. And give us some contrast here. Yeah, that's a lot of contrast. That's good. All right, so now you can see this region much better, and if we back out, you can see it in the context of the Orion Nebula. And, of course, the endless satellites. We have an endless parade of satellites coming through Orion, which is all right. That's a nice quote by Shakespeare. Thank you, Michael. Ray says he's missing chat messages. How can that be? They come through in Facebook, and doesn't matter whether doesn't matter who you are or what you're looking at. If you're in chat and you see the chat, you see all the messages. I'm not sure.
He had trouble with Izabela's messages in particular.
I remember that. Ray, do you have any idea who it is that you're missing?
Building up nicely now around the 13th pearl.
Ah. See, we got these additional objects down here that I think are very interesting. You know, and I'm speaking in particular of this right here. See those guys right there? I don't know what those are. Oh, look, I made a heart. So, I'm not sure.
Ray says he doesn't even see Izabela.
I thought we narrowed that down to a different ID or something, but he should be able to see him because it's a public chat.
Yeah.
We just had a UFO fly through the building. You see that? It was actually,
I missed it.
It was actually like either a spider or a moth, but it's only 8 Celsius out there.
Yeah, I wouldn't think so.
No, we still have insects out there. Okay.
I don't know what to tell you, Ray. He says there's other names that I mentioned that he doesn't see.
Interesting. I don't know why. Ray, it's a public chat, so no one's being blocked. There's nothing going on there. Izabela says, I think you can make a new account connected to your main one. That would solve the missing chat. Yeah, I don't know. I mean, to see the participant list, you have to click the 3 dots at the top right and click on participants. The problem with that is it doesn't show you all of the participants, Ray. It just shows you the ones that YouTube wants to show you. I mean, people, you can put in 10 chat messages and YouTube might not even show you as a participant. It's I don't know how the algorithm works, but it's really stupid, to be honest with you.
Sometimes if somebody hasn't made a comment in a while,
yeah,
it can not show them.
That's correct. Let's zoom in now on here again.
Well, I thought Ray has a wrench. I thought that helped him show everybody.
I would think so. What's going on here? Oh, no one there. Hello. Okay, so let's zoom in on this now. All right, so look. Now you can see this beautiful little dividing line. It's almost like dividing ventricles of a heart. And you have this blue nebula right here and this blue nebula here. And then this guy is a reflection nebula. Now, it's also blue, but you can't see that it's blue because it's very bright, and so it saturates. But then you have this brown dust right here blocking this nebula from showing more brilliantly. And what's behind it is more reflection nebula that could very well be tied to this nebula just being blocked by this, because it's a 3D universe. Okay, everything. Sometimes things block other things. You can see my hand back here, but you can't see over here, right? Because something's blocking it. Well, we could be seeing the same thing here with the 13th pearl, the rubber stamp, NGC 1999. Yeah, and you look and you see these beautiful clouds that look just like clouds in our atmosphere. The only difference is they're light years long. This cloud, like from like here down to about here, this is about 24 light years long. That's huge. That's a massive amount of cloud. You know. So that's just something else. All right. All right, and this is again, we're gonna keep this as Orion Complex. All right, we've done 13 here. We'll do 14, and then we'll stop.
I'll zoom in on it before we move on.
I just was. Didn't you see me? It's right here. I was zoomed in on it.
Or like it.
Look at this detail right here. I think that's really cool. In fact, I'm going to do something. I'm going to take down our brightness a little bit to soften it up just a bit and work it backwards so we can see some detail pop in.
You
Wow,
barely see the little black notch there, just to the right of the star. That's the void.
Yeah, actually, I'm going to try and see that more. Okay. Now, if we zoom in on this, you'll see the black void right here. That is literally exactly what it looks like. So we caught the whole void, and nothing but the void.
What they also call the rubber stamp, I believe.
You got it. Okay, so now that we're there, we'll let it decide what it wants to have for processing, and then we will further increase it to make it even better. All right, so color correction, and we're gonna pull back. This vertical line says black on it. This is the black level. So the further to the right you go over the data, which is here, the more dark it becomes. Okay, and the further left you go, the less dark it becomes. But I'll give you an example. Okay, you see how this looks, right? And I'm gonna bring back our cloud structures here. Okay, so you see all these cloud structures here, all the detail in there, right? And you say, well, how come I can't see those in a light polluted sky? I'll show you why. Because a light polluted sky does this to your image. Okay? It does that to your image. How can you see the subtlety of the cloud when you have light pollution that's disrupting you? You need to have a dark sky like we have here to do this. And now look what you see in the dark sky. I think that's really cool. Oh, and I have to tell Izabela, I did not put your table of contents into the last video yet. My mistake, I'm sorry. I'll get that done tonight. After this. So there we go. That's really pretty. Alright. So now, here's the Orion Nebula at the top. We can actually mosaic this with the area below it like this. And if we were to then move to the left, we could then take another image and another image and just go on and on. But we're just gonna actually stop here at 18. We're about to finish out the 18th one on the 13th pearl, and we'll pause it. And I'm going to keep it as the Orion complex, and we'll save it here. So there we go. I saved the astronomical FITS file format, which is all the raw data, untouched by any processing like I'm doing here. And then we'll save it exactly as seen here. All right, and this will be there just like you see it. All right, it's heading up to the server. You can go check it out at SkyTourLive.com right down below. And in SkyTourLive.com, you can scroll down and say, show me the really cool pictures, take me to the really cool pictures. And you can read there, and it tells you how to access all of our photos for yourself and download them and use them on your desktop or what have you. There's no limitations. You just can't sell them. All right. So now, one of the things I'd like to do is I would very much like to take this opportunity to move us to another object that's my favorite, one of my favorites. I'm hoping that we can see it. I'm rushing Orion, just so you know. I'm rushing Orion. Now, one thing I just did want to notice is Ronald there. Okay. Izabela has a personal session coming up for all she's done for us. She's won a personal session. And Ronald from ERRT Radio has also. He's done a lot of work for us in the background. So he's won a personal session. So I'll be doing those in the near future with them. But you'll all be there too, because it's going to be a stream where they're with us on the air, and we're going to let them guide the stream and tell us what they want to see. All right, and that'll be nice. So Izabela's will be coming up. And that's when she's ready. Alright, so now I do think that it's time for us to move. So I'm going to right now. I save this out. And oh, it's so beautiful. There we go. And now we're going to our night vision mode. And we're going to move now to the beautiful gossamer witch's head, if we can see it. What's the Angel Nebula? I just saw this. It said Angel Nebula here. Didn't you see that?
No, I didn't. Sorry, I was doing something.
It's weird. I just saw Angel Nebula. Wow. Okay. Unless it's up here. I will get to our... There it is. Angel Nebula. Okay. Well, you know what? Let's try it out. That's something new. Sure. And let's hopefully be able to see it. So we'll go there now and see if we can see it. Looks like we can. All right. All right. Oh, look, there's a nebula right there. That's cute. All right, let's zip west a little bit. Center it up. All right. Make sure we're pretty centered up. It doesn't have to be perfect. Oh, that's not. That's a little off, but that's fine. We're actually zoomed a little bit. That's why. So let me zoom out a little. Okay, here we go. All right, so now we do this again, and there's the Angel Nebula. Now let's go back to the east a little. And it'll be interesting to see what this is. I've never seen this before. That's what I love about the universe, you know. We can always find something we haven't seen.
This is NGC 2170, right?
That's correct. All right, so let's go confirm that.
Well, wait.
Angel Nebula is...
you need to shoot a deep exposure of this, Mark. This has some amazing emission nebulosity, reflection nebulosity, and dark nebulosity.
Oh, man. All right. Well, we may never get to... Well, we will. All right, let's try it then. We'll do it. I'm at 300, so I'm going to go to 350 on our gain. All right, and I will take us immediately. We'll do a... we'll try a 45-second shot. Because we've been tracking now for a while, so we're good. We're stable. And then we'll come out and go into our stack. And that's the Orion shot we just took. You watch this progress bar down there on the right. That tells you where we are in here. This is in the buffer. It's not affecting the current exposure. Right now that's being captured on the sensor. And once we count down to 0, it's going to be read off the sensor and thrown out into the empty space, which is right there.
2x2 arc minutes, so it may not show very well.
All right, well, we'll see what we get. Let's see what we get.
I'm going to send the...
we get satellite. Oh, look at... We got a lot of stuff going on in here. Holy cow. See that? Look at all that. There's a reflection nebula here, 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 all throughout this whole region. Look at that. This is actually a pretty good size. Yeah, let me
I think this might be one for when we got some focal length.
I'll bet it's true. Oh my. Indeed it is. Let's see if we can do it some justice while we're here.
That's a crazy picture.
It is.
Here's what we're looking at, folks.
Now we're taking an image with a system that's 4 full moons across by 3 full moons tall in field size. So it's not the best system to take pictures of small things with, but it's okay. All right, let's drop this down and then pull it over.
You're actually in Monteceros now.
Yeah.
Boy, that's something else.
It's something. Let's
Some of the gnarliest looking dark nebulosity yet.
let's add some enhancement to it as well. Let's zoom in a little bit. That gnarly nebulosity he's talking about is right here. That's something else. That beautiful reflection nebula. And when we say reflection nebula, we're talking about dust that is scattering the light of nearby stars. And that's it. That's all there is to it. There's no chemical actions going on. There's no ionization going on. It's just the simple scattering of light by the dust. Shine a flashlight on dust and you can see it in the air. It's because it's scattering light back to you. You can also say it's reflecting light. That seems to be the jargon that astronomy uses, but it's technically scattering. Hello, Dean. Dean is with us. Dean Bostador, how are you? All right, let's pull this out. See if we can get some more data. And we're at 350 gain right now. And we're only doing a 45-second exposure. This, in a private stream or in one of the personal sessions that you may get, you know, if you do tier 4 of our Patreon, you could tell us how long you want to do an exposure here for something like this. Hey, Ronald's here. Hey, Ronald. And Michael Galea is with us. Nice to see you, man. We can safely do up to about 2 minutes with our scope without having to worry about issues with the guiding. But sometimes the guiding is a little rough because of the wind that might happen sometimes. Yeah. By the way, everybody, ERRT Radio is Ronald. Ronald is one of our good friends of SkyTour LiveStream. Does a lot for us in the background. That's why he's won himself a personal tour. And I know you didn't hear about it because I was telling people privately about this. But we'll be doing public things as well. But another thing is, Ronald is having a birthday today. Oh.
Uh-oh.
And he just went, oh no, they're gonna tell me. Oh no. Yeah, that's right, Ronald. You're in the hot seat now, pal. So everybody, wish him a happy birthday.
Happy birthday, Ronald.
We should sing happy birthday to him, except, and the worse we sing it, the better. You know, happy birthday to you. You know, that kind of thing. Okay. Let's unzoom that. Let's do horizontal axis. There we go. Okay, now let's pull stuff in. I sing it in my glass. It's like, happy birthday to you, Ronald. There you go. You're getting all the birthday greetings there, Ronald. Hey, you brought it on yourself. You were born. Your fault.
I think your image is actually rotated about 180 degrees to that image I sent you.
Yeah, there's no
The
telling.
dark nebulosity, the real
It's right here.
spiraling nature of it. Yes.
You can see it now when you do this.
Yeah.
Oh yeah. This was actually a good little object. I like these little objects that we find like this, you know. Look at the details in this dark dust. It's starting to come out now because as we've stacked only 9 images, but as we stack these, you can start to see the dark dust starts to stand proud above the noise, and that's what we're waiting for here. Hey, Sam S. How you doing? Judy M. Looks nice.
Can you darken that or do anything to pull out the dark nebulosity?
Yeah, that's what I'm waiting for another couple of these to come in.
Oh, okay.
Because otherwise, like if I try and darken it now, all right, you'll see that it's not gonna help too much. Oh, actually, it does. Look at that. We see it in silhouette against this stuff, but I want to be able to show this stuff too. And it's a little noisy yet, so if I give it to Tilt to do it itself, okay, it gets close, but
Nescovid, that's a pretty heavy question, no pun intended.
Hey, Nescovid.
Maybe I am intended. Oh golly.
Truth is, in terms of looking at the amount of mass we understand, looking at all the known galaxies, estimating the amount of dark nebulae and stars and solar masses of stars, we've come to the conclusion, and this may be changing, that there hasn't been enough mass yet to have formed and caused the Big Bang. It's almost like we haven't got to the point in our understanding of the universe where we can say, yes, the Big Bang happened because there's enough mass to have created it. We just don't have enough mass. However, that has led to other theories, Nescovid, and that is that the universe actually may be one of several. And our universe might be an offshoot of another main thrust, and together the mass would sum to what could be something that constituted a primordial amount of matter. And I also have to be very, very clear here. Just like with black holes, talking about singularities, infinitely small points in the middle, no one believes that the primordial superatom was actually a tiny, infinitesimally small object that blew up. Okay? No one believes that. It's just, it has to do with how our physics works and how our equations and how our calculations of gravity work and forces, right? Whenever we, if you've taken physics classes, you know that they tell you the force of gravity is calculated as if it's acting at the center of an object. So when we calculate the force of gravity, say between the Earth and the Moon, well, the equation is capital G, big M, Earth, times little m, Moon, okay, over radius squared, distance between them. And how's that distance measured? Center to center, okay? So that leads you down the path to say, oh, well, gravity is acting at the center of an object. Well, it is, but it isn't, right? I mean, because the gravity changes all over the Earth. The gravitational force changes all over the Earth depending on how much mass is beneath your feet, right? So it varies. That means that the primordial superatom, when the Big Bang occurred, we're doing the same thing with that. It's not a tiny, infinitesimally small point. That's just how our physics operates, and that's how we calculate the mass and the energy involved. But the fact is, we know it was a massive object and big. Okay, same with black holes. Okay, we talked about this yesterday. Messier 87's black hole. Messier 87, that's 44 million light years away, right?
something like that.
Okay, Messier 87 has a black hole several times the size of our solar system in it. That means its event horizon is several times the size of our solar system in diameter. So that is telling you that the inside, beneath that event horizon, that's where all the action's happening in a black hole. What's at the center of a black hole? It almost doesn't matter, because that's not a pun, but it acts like it's at the center. We calculate gravity from at the center of things. So it's actually a mathematical construct, which is why that has crept in to people's psyches, and they think, oh, how could there be an infinitely small atom that's so massive? There isn't, and there can't be. And no one believes there is. Right? But it's just how we calculate things. You know, so that goes to your question that you were asking about the calculation of matter, because we look at all the mass in the universe that we know of, and we find it doesn't add up to have made enough to make the Big Bang. And we're still there, actually. We don't know the answer to that. I don't know the answer to that. Daryl doesn't know the answer to that. Stephen Hawking didn't know the answer to that. Kip Thorne doesn't know the answer to that. And no cosmologist can tell you how much mass is in the universe. We can estimate based on what we see and what we project. I'll give you an example. We see out to about 13.8 billion light years, right, in our understanding of the universe. Truly about 13.6, okay? And the fact, though, is that the universe is not 13.8 billion light years in radius, okay, nor 27 billion light years in diameter, okay, from that, doubling it, okay. It's actually 91 or 92 billion light years in diameter. And we don't know what's way out here, okay. We only see out to the cosmic microwave background. We can't see past and see anything else. Now, how do we know it's bigger than that? And this is a little aside, but think about this. The universe is expanding, right? Hubble came up with a constant called the Hubble constant. They named it after him because he discovered it. And it was the speed at which the universe was expanding. And they tried to say it was a constant speed, and they used calculations. They figured out the size of the universe. The expansion rate was a certain solid rate. It didn't change until it did. Once they started looking at data from the Planck telescope and other telescopes and other analyses, they discovered that no, the universe is expanding still, but it's accelerating as it expands outward. It's like the explosion is still underway, accelerating outward. And we know that the explosion happened 13.8 billion years ago. So what's happening? And that's now I think of it, and Daryl, I think, is kind of on board with this a little bit. I think of it as sort of a little bit of a fudge factor because we don't know the true nature of it. But they call that dark energy. It's a repulsive force that pushes everything around it away from itself. Okay? Every object being basically pushed away from every other object. That's on global scale. All right? But on the smaller scales, like the scale between galactic clusters like our local group, that scale, all right, is something where we can see galaxies coming toward each other, merging and moving through. Andromeda is going to strike us eventually and change our galaxy forever and turn us into something that we're not. It's going to make us into a different type of galaxy when that happens. But on a whole, right, the universe, the galactic, these local groups and the other groups, the galaxy clusters, are speeding away from each other at an ever-increasing rate. And so it's an accelerating universe. And no one knows why. But to understand that, or to actually work with it, they came up with the concept of dark energy, which we mentioned, which is that repulsive force, which pushes everything else away from itself. And basically space itself is pushing itself away from every other object. It's a very, very difficult concept to follow, but it is exactly what they are saying is happening, as best as they can tell. So you see how deep your question goes? Because we can't see all the mass that's out there, so we don't know. what's going on deep in the universe. Because we can't see it, we never will see it. Because we're stuck with the speed of light. And now I'm being quiet for about 10 seconds. Look at this. So you can see some of this now, Daryl.
Yes.
All right.
Can you pull it out anymore?
Yeah, I'm going to work on that. I'm going to see what's really here by throwing this up here. Okay.
27 images now.
Yeah. All right. So here you can see. This is actually quite a detailed region, isn't it? You can see that. I actually threw this other histogram up there to show. Look at all the detail of this dark nebula. This is exactly the thing that's going on here. This star is in a reflection nebula state. Look at the bands of reflection nebulae here. Okay, these are literally denser waves, basically, of dust that the starlight is refracting. I'm not sorry, refracting, scattering off of. And so, it's very interesting. So,
I wonder why they call it the angel.
I think because it has what might appear to be wings in there. I mean, I think in your shot it kind of showed some wings, right? It sort of looked like that. This might be the body. I don't know.
Yep, this is serendipity for you here.
I absolutely love it. Yeah. Oh, Carolyn Corey's calling me right now. I can't talk to her right now. I'm streaming. Carolyn joined us last night on our stream, actually. She came into the chat. Maybe, that's too bad, actually. If she was in the chat again, I would invite her to come on with us. Carolyn Corey did the show, the movie, Tear in the Sky. It was a beautiful movie about the search for, the scientific, in fact, search for extraterrestrial life. And I think that was really cool. What she did, I actually sat and watched it. She's doing another one, and that'll be really interesting to see what's involved there. But she's a real sweet person. This is stunning. Even now, I'm seeing more stuff here, Daryl. Look at this.
Yeah.
I'm going to zoom in on that. And I'm going to drop down the noise a little bit. I'm going to cut the noise. You can see some of the noise here. But that's because we're at 350 gain. I'm going to drop the noise a little. Oh, look at that. There's a lot going on in here. This is one complex location, man. What a beautiful, beautiful shot this turned out to be.
Need to remember this one for future reference.
Yeah. Izabela, remember the Angel Nebula. This is actually it will be remembered because Izabela put it in the table of contents. This is NGC 2170.
Okay.
Yeah. And let's come back here and let's color correct one more time because we got a little too much blue in there. There we go. Now you can actually see. Now we'll throw this up one more time to pop the detail in there. Look at that. Wow. That's really pretty. Wow. I'm going to write that one down. Okay. Okay, so we have 27 frames. We'll go to 28, and then we'll continue moving on. And if we see something else along the way, we're going to stop and check it out. This will be called The Angel Nebula. Not AIM Amgel. Alright. That's nice. Alright. So we'll save that to Angel Nebula. Pull that out for now. All right. I think I did that, but I'll do it anyway. Yeah, okay. Good. All right, so that one is a keeper and one to remember. Amazing how what's there, and you actually just do a quick look, you only see the tiniest little hint of a potential nebula, right? I think that's pretty cool. All right, so let's now head in here again to our location and just see what's NGC 2149. It's a reflection nebula. Okay, well, we're in Monoceros now, like you said.
Yep.
We'll just zoom out a little bit. This is cool. And we're going to come to Rigel now. Actually, before we do that, let's see if we can... I knew about this planetary. I wondered if we could see it. IC 418. Well, we're going here anyway in a bit, so let's just head on this way and see if we can see the Spirograph Nebula. It's not that large, but we'll try it. Why not? If you notice where the telescope's pointing, it's actually gonna be pointing, you know, more this way, so we're gonna be fine.
Mark, excuse me a moment, please.
Yeah. Okay, I think it's right there. I could be wrong, but I'm gonna see. Okay. I think it's small. All right, we shall keep going. All right. We'll keep moving because I don't want to waste time on an object that's going to be so small that you're going to have to say, "What's that?" And in spite of all the dark nebula that's around, interesting, huh, that there's galaxies. We have a galaxy right here, NGC 1954. It's an SC. That means it's got spiral arms, but they're kind of loose. And then this one here, this is NGC 1889. It's an elliptical. And those just tend to be either round or elongated collections of stars with nothing else in them. Very boring. But how they happened probably wasn't boring. How all their gas and dust got stripped from them could be due to a collision with another galaxy. And then right here, right away, we are up for the Witch's Head. And the Witch's Head is just another location. It's an extensive nebula. And we'll try to take one good shot of one section of it. And then we'll do a composite at another time. Let's see here. We'll go here. let's pull in. Yeah, that's the central part. What I'd like to do is take us up to here. Take us up to the witch's, I guess that's the hat? I'm not sure. Right up there. Alright. So, I'm going to just go to that spot in the sky. Okay. And we should see this shape vaguely in the view here. Alright, let's it's right there. I have to just move us to be able to see just the... There we go. Okay, and now we're gonna head east a little bit.
Did I see the witch's chin a minute ago?
Only in Stellarium, I think.
Okay.
I think head back to the west, actually. That looks like it there, too. I remember this star. Is that Crucial Jalza? Let's go see. I think that star is this star. If so, it's right there. So I'm going to head back here again. You can see it there on the screen. Well, I should just take a photo and see where we're sitting. So I'm going to do a 35-second shot and let it do it. And it doesn't matter that we are not hooked into our thing here yet, our guider. We're okay with that. I think we'll just have to clear that one. All right. Yeah, okay, so I thought so. So it's right there. With a stupid satellite. That's all right.
Witch's chin.
That her chin?
That's her chin.
All right. All right, well, I'm going to...
Her lower lip and
Okay.
top of her nose, or bottom of her nose, to the very bottom.
Okay, so here's what we're going to do. We're going to move down just to bring this to the top here. All right. So we'll use that satellite as a guide. All right, so let's go here first. That satellite will be in there if we do this. There it is right there. So we'll move the satellite up to the top of the screen.
That's a slow mover.
Yep. I wrote a program to calculate how fast satellites move at different altitudes. So I should be able to tell how fast a geosynchronous satellite should be moving in our field because we're following the stars. And that's actually a little more like it, actually. But it's even slower than that. And very faint. This is certainly not. This is too bright. Okay, let's do some imaging. Let's do 55 seconds. We're locked on. We're guiding. I'm tempted to do like more than that, but I don't want to. All right, here we go. We are stabilized and going, and we'll get into the stack. The live stack is right there. That's the first image we took. And we move this to the top, and we're going to clear this. All right, so the witch's head is a large patch of dust to the right of Rigel. Rigel is a very bright star, and it has a lot of ultraviolet radiation. And the ultraviolet radiation, of course, spews out and so forth, but it has a lot of, very high frequency blue light as well, being a hot blue star. So that dust is, again, scattering the light from Rigel. And it is Rigel that's powering that nebula. I say powering it, causing it to scatter light. Here's the first one coming in. Oh, yeah. Look, you've got satellite there, satellite there, satellite there. Let's try and adjust that right. There we go. Look at that. So this is
like the Wicked Witch of the West standing on her head. What was her name? Margaret Hamilton?
Yes, Margaret Hamilton played the witch.
Yeah.
I purposely watched Margaret Hamilton in a different setting so that I could see a little better what she was, because I thought of her as this evil woman. It's like, wow, she was very good at it, so good at it. As a kid, I thought it was real. She was really the witch. And so when I saw her in other things, I was like, oh no, that's the witch. And it turns out, no, she was actually a very accomplished actress. Let's do this.
I want to say she was on Mr. Rogers once.
Oh, I bet she was. Are you the Wicked Witch of the West? No, I'm not the Wicked Witch of the West. Oh, certainly. Well, good for you. We're going to go to the Magic Kingdom.
Izabela has a question of you.
Oh, yeah. Oh, I see the question mark. Thank you. Well, if you think it's a stupid question, I better not read any further. But there are no stupid questions, as I've told you. I read somewhere that at a certain age, stars can split. And this is how some binary stars are created. Is this true? No. Stars don't split like amoebas. Amoebas split like amoebas, but stars don't. Stars are born either as a binary star, and what you're thinking about might be a confusion with the way stars are born, because in a stellar nursery, say, where there's a lot of gas and dust, you could have two blobs that start rotating around each other, all right? And there could be one logical blob that does pull apart over time for some reason. There's no reason why that can't happen. But you can, as they're young, hot blobs of gas, you might, if they're rotating fast enough, you might have them pull away from each other and then orbit each other and form binaries that way. That's a possibility. But stars do not split to become other stars. As Rascally Rabbit says, there's no cellular mitosis going on there. And by the way, hello there, Rascally Rabbit. Hello, Sean Paris. And she was on Sesame Street. I remember that. Margaret Hamilton was on Sesame Street. I remember that appearance. Well, she had an image problem, see? Because everybody thought she was this wicked old lady. In fact, she wasn't. She was a sweet person. It was very hard for her to play an evil woman. Okay.
Hello, David Schmidt.
David Schmidt is with us from Thailand. Hey, David. Nice to see you. Let's see how much more data is waiting for us out here. Yeah, we're getting pretty much all of it. See how this is starting to tint a little blue? The longer we go, the more blue you'll see. See, you see a lot of blue now. So that's really cool. Hey, Hunter. My son just got home. Very nice. Very nice. Very, very nice. He was a Russian invention. Alright. So we've done 5 here because we're doing 55 seconds. And I want you to notice how the guiding is going so beautifully. And so I can prove it to myself, I'm going to zoom in. Oh yeah, look, stars are round. I love it. Stars are round. So the way guiding actually works, guys, is that the telescope is following the stars, but it's a mechanical device. It's not perfect. Okay, there's actually what's called periodic error in the drivetrain of any telescope, and that periodic error can cause us the thing to go ahead or behind or possibly up or down. During the actual commission of a photograph, or actually taking a photograph. So a guider makes note of that, knows where those times are, and when it sees the stars start to pull out ahead, it starts to guide, and it actually moves the telescope to keep that star right in the crosshairs. It's an auto guider, okay? And you can't see that telescope, but it's literally up on the other side of this one, and it's about this long, and it's actually pointing in the sky, and it's doing all the work. The telescope is just a dumb telescope. It's following the stars, and the guiding system is telling the telescope to inch ahead a little, come back a little, inch ahead, wait, go up a little bit, come down a little bit. And we see what it's doing when we look over at this. This is our drift graph over here. This is the alignment history, shows you the drift graph. And here you can see, I'm trying to get this one to come up. There we go. So you see all those plus signs? That shows you the fraction of a pixel that the telescope is moving in order to guide and keep the object in play. By looking at this, it tells me how well the guiding is going and whether I should make any adjustments to the guiding input. I can make computational additions to the guiding input. But in this case, all right, you look over here and you can see that everything is pretty much on track. It's actually probably as good as it can get. Yeah. Okay. All parameters are nominal. Okay, we are at 9 stacked right now. Listening to the music and looking at these beautiful objects come in, it just makes me want to be all philosophical. It's just really, this something like this is the reason I became an astronomer. This is where it's all happening. This is the reason there's life in the universe. This nebula right here is one of those things that shows you why there's life in the universe. It's cold and it's dark. And when Rigel goes supernova, I can make a prediction what will happen. Rigel will explode, and it'll pump out all kinds of radiation initially. And then over time, maybe 100 million years, 200 million years, the shock waves that hit this dark cloud will cause compression in various spots and cause new stars to form. And of course, with those new stars will be new planets. And then without Rigel, with all that ultraviolet radiation, well, then this region might become a fertile location for life. Right now, it's not as fertile as we'd like it to be. But it will eventually be a fertile place to live in the universe. We found one, we're on it. Okay, 11 stacked. You can see the count right here. You can also see the count right here. Make sure you're on 1080p, by the way, so you can read all the little details. If you're not on 1080p, you may not see it. It might look kind of fuzzy to you. Nescavate, I ask a question. He says, is the Witch's Head part of a prior supernova remnant? I actually don't know the answer to that question. It is a dust cloud. So to ask about whether it's a part of a supernova remnants generally are emitting light, not scattering light, you know, because they have a chemical consistency of the former star's contents. All right, hydrogen, neon, oxygen, and other elements. And we don't see that here, so this to me looks like a dust cloud to me. So I would venture to say, as an educated guess, as an astronomer, that this is probably a dust cloud that was formed when supernova went off, but it's not the result of supernova. It's it's probably been pushed and compressed in space, maybe by Rigel itself.
Yeah.
And so that dust is being snowplowed by the radiation from the star and being compressed. And eventually, when Rigel goes supernova, and maybe before, there will be a certain amount of stellar formation and planetary formation that is driven by that process.
I suppose if you took the long view,
Mm-hmm.
you know, that it's sort of a supernova remnant. It's left over from a supernova remnant, left over from a supernova, left over from many supernovas.
Yeah, I mean, all the dust was generated by supernovae in one way or another. That's true.
Yeah.
You know, but this is not a supernova remnant like the Crab Nebula, like, you know, the Veil Nebula. It's actually a dust cloud that's hanging around. I mean, Barnard's Loop is a supernova remnant. This is not a supernova remnant.
Yeah.
But it is the result. I mean, every dark dust cloud in the universe is the result of a supernova, a plethora of supernovas that are going off in that area. You know.
Sure.
Think about it. It's all 3D space, right? So you have a supernova goes off over here. A supernova goes off over here, over here, over here, over here, over here, and those motions of all that material going every which way hits material, causes it to twist and move around. Electrical currents get imparted into this material, causing them to twist and spindle, like in the Veil, all right, that we see. So there's all kinds of other processes going on out there that are just absolutely fascinating to understand. You know. All right, we're going to go to 15 on this, and that's going to end right now. So I'm going to pause it. Actually, I'll resume it for the moment, because then I'll change the name. All right, this will be the Witch's Head. What?
IC 2118, also known as Witchhead Nebula,
Yeah.
due to its shape, is an extremely faint reflection nebula believed to be an ancient supernova remnant or gas cloud illuminated by the nearby supergiant star Rigel.
Dust cloud, it was supposed to say.
You know, well, it says it might be an ancient supernova remnant
Well,
or a gas cloud.
yeah, I think it's a dust cloud. And I think Rigel shaped it. I mean, Rigel's only been around for a few tens of millions of years. You know, so there's plenty of time to shape the cloud.
Radio observations show substantial carbon monoxide emission throughout parts of 2118, an indicator of the presence of molecular clouds and star formation in the nebula.
Mm-hmm. Yeah.
In fact, candidates for pre-main sequence stars and some classic T-Tauri stars
Mm-hmm.
have been found deep within the nebula. We looked at T-Tauri last night.
We did, and I think it's going to be interesting when James Webb takes a look at this, if they can get it to do that.
Molecular clouds of IC 2118 are probably juxtaposed to the outer boundaries of the vast Orion Eridanus bubble, the giant supershell of molecular hydrogen blown by the high mass stars of the Orion OB1 association. As the supershell expands into the interstellar medium, favorable circumstances for star formation occur. IC 2118 is located in one such area.
Look at this stuff. Yeah, this, again, with Rigel's influence, the compression of this material is going to cause clumping and thus gravitational contraction. So yeah, it doesn't surprise me. But the denser part of the nebulas are the things I would like to look at. Like what's going on right up in here, you know?
You're going to take a picture of the lower part, her upper part of her head?
Maybe. It depends, because I'm thinking about possibly going over to Hubble's Variable Nebula. Because this is a very interesting part of this nebula.
I did find one way that binary stars can split.
Oh yeah?
If they are a weakly interacting pair, not tightly gravitationally bound, another star can pass by and basically pull one of them away from the other
yeah.
one.
That's actually wasn't the question, I don't think. It was, can a star split and become two stars?
Yes, I know.
Okay. Yeah, binaries that are yes. Example, a quadruple star system is unstable unless unless it's like Epsilon Lyra, where you've got two stars going around each other and then two stars farther away going around each other, and then that whole group going around each other. Okay, that's the only stable way. But if you have them in close proximity, they're going to have extremely complex orbits, and sooner or later one's going to get rejected from the system. It's the n-body problem, trying to solve that. When you get up to 4, you can do it. When 5, 6, 7, you can do it. You get to about 9 or 10, and you get to members of the Pleiades cluster, where there's 100 members of the cluster, plus or minus. It's a tough slog to calculate, even with a computer, all the outcomes of the potential interactions from their gravitational forces acting on each other. You have 100 members, and you got to calculate the force of 99 other stars on this one.
Oh yeah.
And then calculate a vector, and do that for the next star, and the next star, and the next star. Yeah, the computer can do it, but it's a tough slog. Even we could do it on my computer here, but it'll work. But I'm not so sure that the computer won't overheat, because that's actually a lot of core processing, and I have 6 cores in this machine.
Yeah. Well, I dare say you could say that's why open clusters tend to come apart over time.
Mm-hmm.
Michael Hedrick has a question for you. Excuse me again for just a second.
Sure. Controversial question about star formation. Yeah, sure. Go right ahead. He wants to ask a controversial question about star formation. Alrighty. Well, this is good because it saved us to get to 21 images here. There we go. We got 21. And I put Witch's Head Nebula, and we'll save it. And then we'll save it exactly as seen. Alright. Now, let's zoom in and check this out up here. I wanted to see this before. Wow, look at that. You can actually see how some of these stars are illuminating the cloud. I imagine they're probably in the cloud. Here we go, look at that. Just so you know, this object has been elusive. I've never been able to show this object very well here in Connecticut because of the light pollution. This requires a much darker sky to see it like we're seeing it now. The subtle detail is absolutely astonishing. So, okay, so let's see. Let's do a... There we go. So you can see the blue color now quite nicely here. And that's the starlight being scattered. And then you see a little blue up here. It's not white, it's really kind of a subtle blue. Alright, so I think I saved this already, and yes I did. And save exactly as seen. There we go, okay. When you get those orange bars, it means that I've actually already done that, and it won't let me save over it until the next exposure. That's good. And I will just save this exactly as seen. I don't know if it's going to let me do that. Maybe not. Let's find out. Okay, not a problem, because I turned off the stacking for this particular exposure. Okay, so this is out there as Witch's Head Nebula. All right, so now we're going to go back and go into night vision mode and check out our next object. Okay, so Orion is right up there now. We have no problem seeing Orion. It's beautiful. Oh, that's funny, Izabela. All right. Now, let's go. I tried to do the Spirograph Nebula down here. This didn't work.
Did you get Michael Hedrick's question?
He was supposed to ask it. I don't. Did it? Oh.
Second law of thermodynamics.
Yeah. The total entropy of a system either increase or remain constant in any in any spontaneous process. It never decreases. How does this work with star formation? That's actually a very good question. And in terms of star formation, one of the things that's going on in the core of the star is it's actually being compressed. So we're seeing that the entropy is as far as the motions of the objects, those motions are under constant pressure, right? So it's contained in a smaller space, so that all causes the temperature to increase, and it's that temperature increasing that actually causes the star to fuse elements at one point. Hydrogen needs 13 million Kelvin to actually fuse into helium. And the process is complex. We've talked about it before. It's deuterium going to helium-4 in the end, which is an isotope of helium. But the process with stars is, of course, they're in equilibrium. The stars are in equilibrium. As they're developing, they can actually have bursts of energy that they shoot out and stuff like that. But once they're on the main sequence and fusing hydrogen into helium, then they're actually pretty stable. and so their outward pressure is counteracted by the inward pressure of gravity trying to collapse it, because they're pushing out as much as it's trying to be pushed in. So that said, I'm pretty, as you can see, I think that the way this works is that we're looking at stars under compression that in the inner cores, which actually causes the heat. Cosmic ray, what are you doing? I'll show that. I don't know what you're doing. I'm sorry. Shows the outward pressure of radiation that's pushing out. As far as when you say the second law of thermodynamics states that the entropy of a system either increases or remains constant in any spontaneous process, it never decreases. That's true, and we don't see that the entropy actually decreases in a star. If anything, it increases because the temperature is increasing. Then it will stay the same when it's in equilibrium. See where we're going? So we have to be careful, though, because in the outer atmosphere of the star is always giving off mass. It's always undergoing mass loss. Our sun's solar wind, in its stable hydrogen fusion state, okay, our sun's solar wind is actually spewing protons and electrons at us. That's the solar flux. Well, those protons and electrons are exceedingly important because they're actually being lost, aren't they? So we're getting a loss of mass. All right. So is that a change in entropy? Well, essentially at the boundary of the star where it goes out, we know that there's a change in the entropy. All right. So it might actually increase once it leaves the star. So I'm not sure if that's going to satisfy you or not, but I want to find something here.
Ray, the comet's only 8 degrees above the horizon here in Colorado. And Marc is
less here.
It's less than Arizona.
Yeah.
And the north wall of the observatory is blocking it.
At the moment, yeah. Okay.
Marianne is here. Hello, Marianne.
Hello, Marianne. Let's try to see if the Seagull Nebula is visible right now. Hey, I already told everybody to tell Ronald happy birthday, Marianne. And they did. They went after him with a vengeance. Very cool. All right. All right, so here's the Seagull Nebula. Now we're going to move over, look at it some more. Ronald told me he's 26 today. But he also has dyslexia, you see. So he swaps the numbers. Okay.
Last time we looked at the Seagull, was it that night? It was rather cloudy.
Yeah, so this will be a nice night, to look at it. It's clear. It's in the clear. It's above the wall.
Yeah.
All right. So we'll let this lock in, and we'll actually do a 50-second shot of this too. I think that would actually make it really nice. Actually, 55 seconds. Okay, we're guiding, and I'll wait for the stabilization to occur. Okay, we're good. And then I'll...
Excuse me.
What? Okay, and then this will come in, and we'll see the last one. So you see the witch's head shows nicely. It really is beautiful bright.
Did you get a birthday cake, Ronald?
Did he?
He hadn't answered yet.
Oh, okay.
I had to get it myself, but I got myself a carrot cake when my birthday happened.
Oh, wow.
I love carrot cake. I found one at the store, so I bought it.
Okay.
That's more like it. I think we're seeing much more than we were the other night.
Oh, yeah. I might have to start this one again because I think I jumped the gun on having it stabilized.
So he bummed a piece of cake at the bar.
Ray, second law of thermodynamics actually does discuss entropy, but it will discuss it in terms of temperature. A hot object will tend to move into the cold object, and the system will balance. Okay, so that's where that goes. So you're both correct. All right, so we have more down below here. See that? We have more down below.
Oh, yeah.
That's nice. Let's see what it wants to do here. So it does that, and then we can actually do a color correction to actually pull out more of the beautiful nebula. Now, while this is stacking up for us, let's go see what else we can look at. I would like to see... I want to see Thor's helmet. I can't wait for Thor's helmet. So we should be...
You know, one we don't look at that often is, well, they call it the little Beehive right there.
Oh, yeah, that's true.
M41.
Yeah.
That's a nice star cluster.
Yeah. Yeah. I want to try something. Oh. This thing is sensitive. Or it's needs a, that's what it needs, okay. Okay, that's what I thought. I thought we were right near it. Alright, so we're going to check out Thor's helmet too. We're going to be able to take a deeper exposure of Thor's helmet than we've ever taken before. So we'll do that right after the Seagull. We can also go to the little Beehive as well, Daryl. I mean, M41's a wonderful cluster.
Oh, yeah. Eventually.
All right, we have Seagull
Very
Nebula
nice
there.
star cluster. Its own right. It's right next to Sirius.
Yeah. Here, let's give this one a chance to shine, shall we? Pull this over a little bit, and here we go.
I think that's much nicer than what we had the other night.
Oh, I think so. I think so. Wish I could dynamically do these stellar reductions, you know, to actually dim the stars to highlight the nebula. But
How much are you zoomed in right now?
I'm only 2% over the you know. I mean, I'm like, if I zoom out right now a little more, you see we already got the border.
Okay.
So we want to go to the, if we want to go to the center and look at this. And take this. It's not. Come on, there we go.
Dark nebulosity, and this is interesting.
It is.
Such a jagged line of it.
Yeah. Yeah, that's really pretty. Look at the. You can see that there's a wall here, and there is a higher radiation impact on the hydrogen gas here, causing it to glow in what looks like brighter. That's because there's a higher density of gas there at that point, so more hydrogen atoms are glowing than, say, over here. So it's a slightly thicker area. You're literally watching the mixing of the interstellar medium. Cosgrey asks, have I tried OpenAI or GPT to process an image? No, I have not. I've not tried either of those. I am a Photoshop guy. Hello, Dan Norton. Thank you for coming out. We're checking out the Seagull Nebula right now, which I'll name for you here. And this is an emission nebula. Alright. And every emission nebula seems to have dark nebula in it. Let me just throw that out there for you. There you go.
What we're looking at right now is the head of the seagull, I assume.
I believe it is, yeah.
Yeah, I think I said this part reminded me more of a parakeet the other night.
Yeah, you did. It kind of does look like a parakeet. Or a really angry parrot.
Yeah.
Now that we know it's a seagull, I'll just pull that out of there for now so we can watch the beauty unfold here, and I can drop this down so you can get a nice look at it. Look, we're catching an additional subtle flow here that we didn't catch before.
Yeah. So the wall, you called it
Like up here?
the more intense part, yes. What's illuminating it? Is it even in the field? You know, you
could be inside the
sometimes-
nebula.
Yeah, sometimes I assume maybe it's that bright star in the middle, but that's probably actually a foreground object.
It could be, or it could actually be a star that belongs there. But the thing is, if that star was causing it, I would think that it would probably light up more stuff.
Yeah.
See, this illumination from here, it could be one of these stars here doing it.
Yeah.
And that's the beauty of astronomy. Trying to figure that stuff out is the cat's meow, right? That's the stuff to figure out. So I like that.
Yeah, well, you know, it's like we know Sigma Orionis is illuminating the wall behind the horse head.
Oh yeah.
And there's reflection nebulosity going on in there too, so
Yeah, right here. Can't miss it.
it's, yeah, well, even in the middle.
Yeah, in there, yeah. A little bit in there. Yeah.
So whatever
Right
is
here.
doing the illumination must be farther in that way.
Maybe. Maybe. Gotta keep in mind that what looks like a dense object to us, in reality, when you get close to it, you can see, for light years. It's not there's nothing blocking it. It's just a rarefied atmosphere, essentially, of a few atoms per cubic centimeter, between 10 and 30,000 atoms per cubic centimeter. Right.
IC 2177, and this is the Seagull's head.
Yeah. We're capturing real subtle detail here. Like, look at how this scalloped front here is. We have these little waves coming down, and then we have this outer area here with subtlety down in here. We have details down in here. It's just beautiful, and there's a lot going on in here in 3D. You know? Whimsical, Michael says, yeah.
Can you go to
Stellarium
for a second? Zoom in. Article I found says HD 53367 is at the center of.
It's Thor's helmet. Sorry. There it is.
There it is. And can you line up on that star itself?
Okay, well, the star itself.
But they don't ID it.
Well, they had to ID that star. Yeah, they use this star as the. They use this star as the one that actually defines the nebula. Okay.
All right. Well, never mind.
All right. But it's interesting how we're catching all this data.
The article, I think, the big bright one you were just looking at, or the one we see in the middle, actually is what's illuminating the nebula.
Okay. Yeah,
It's a triple star.
Okay. Are we seeing all three components, or are they spectroscopic binaries? Wow, look at that. Now that's stunning.
So an additional 533.67b, that a separation is 0.6 arc seconds. So I think they're probably all together there.
Okay.
And evidently that is what's lighting up the nebula.
Interesting. I mean, I've never checked to know. I have thought I'd never seen the Angel Nebula before, but I may be standing corrected because Robin Curtis says that I have an image of the Angel Nebula in the database, apparently. Maybe NGC 2170 is what I called it. How about that? All right, Robin. I stand corrected. I will look and see. I mean, it looks like it. It does look like it. Oh. All right. Okay, we have 16 stacked here. Let's do this. Let's move over a little. I never called the Angel Nebula before. Okay, so that was NGC 2170 then to me all the time. Alrighty.
I don't remember ever looking at that.
I know. I think Robin's lying to us. Look at this. This is really pretty.
Yes, Izabela. She's I see her two places above you, at the bottom of the chat.
She's above Sam S's comment. Cosmic Ray, the URL to the doorway to the database, if you go to SkyTourLive.com, scroll down, and you say, you know, I want to see cool pictures, you click that and it'll take you right to the entry point. All right.
And that's just your server, right?
That's the server. I think that's what he's talking about.
Yeah. Give me just a second.
Well, he's saying database in caps. That's our server. As far as the database, we don't have the database front end done yet, so we're just doing queries, SQL queries to get the data we want. We do have the database. All right. So that's you know, if that's what you're asking about the database versus the actual files, we don't have the front end to the database ready yet. But we have over a year and 2 months of data in there now. Okay, we're at 18. We'll go to 19 and then we'll stop. What? Okay. That was interesting. So, Cosmic Ray, yeah, that's just a file directory. If you want to see the actual database, we're not ready to release that yet, but we want to build a front end to it, so you can just go to our site and start typing in what you want. We have many observations of the same thing over and over, and so what you could do is you can take those and do some actual research on those to see if anything's changed over time. The common man at the moment can't reach the database. That's only that's our database for testing. Even Daryl can't get to the database right now, because it's literally something that we're trying to build the front end to right now. If anyone knows how to build front ends to the database to make them nice programs, speak up. We could use you.
Not me.
Okay, we're at 20 here. We're gonna pause this now and save it. All right.
A nice picture too.
Yeah. All right. There we go. So we have it, and this is the image you will see when you go there. I'll just show you. There it is. That's the image of the seagull that's up there right now.
Nice.
Yep. And we can pursue getting that even better processed. Okay, that said, that takes us now to the next object.
Or his helmet?
Yeah, I gotta see Thor's helmet. It's right nearby, so and we can actually expose it for a lot longer now. This is something that we've been lacking because we didn't have the guiding capability, but now that we do, we're going to go there. All right, so
Cool.
yeah, and it's literally right nearby.
Yep. This is a textbook example of a Wolf-Rayet star, folks.
Yeah, that's right. There it is. Now it looks kind of small, but when we actually do a good number of exposures on it, you'll actually be able to see a lot of detail. All right, so we're going to go a little to the east. Well, I try and pull out the color tonight because there's actually a color in there. There's red filamentary streaks in there that I want to catch. I can see some right here now, but I actually want to get it all. All right, and we're gonna do a 55-second shot of this one. I can tell you that. I really want to do longer, but I don't want to make people wait and watch that.
Well, there it goes. All right. Yeah, it looked like your Starlock guide wasn't working for a second.
Yeah, it takes 12 seconds to acquire.
All right.
And here, it has no trouble acquiring, actually. All right, so it looks like we're pretty good to go here. And I will now go for it. So out of night vision mode into live stack mode, remove the last stack. Ah, that's just pretty. That's up on the server now, guys, if you want to go check it out. Ray, I'll let you know, like I said, if there's anybody out listening who knows how to do front ends for the database. I was a programmer for many years, and I'm too busy doing everything I'm doing here. Plus, we got a third observatory we're putting together. And I just don't have the time to build the front end the way I want to. Robin Curtis is working on the front end as well, and but if anyone can help out to make it happen sooner, that would be wonderful. Okay, so let's go see. Are you ready? Here we go. Oh, look at that. I'm going to zoom in and see if we need to refocus. There's so many stars here that they're annoying.
Yeah.
All right, and we're gonna refocus here. Okay, so let's go.
Looks awfully grainy.
Well, yeah, I mean that's unfortunately what happens when you have so many stars. And that was only the first exposure. They always look grainy with the first exposure. Okay, so here's what we're gonna do. We're going to
if you're shooting longer exposures,
yeah.
it looks like you changed again. It was 55 seconds, wasn't it?
Yeah, but I had I'm doing a focus run now, so I changed it back to 1 second.
Very good.
Yeah.
Would it help the grain if you turn down the gain?
Yeah.
All right.
Yeah. However, if I turn down the gain, then we won't be able to see the detail. It's a subtle difference, you know, but all right, multi-star, full width half maximum. Okay, we have 54 stars to choose from. We're gonna scan in, and you'll see us develop a. Oh, that was a mistake.
Oops.
Yeah, that's okay. It's not gone. It is just. It's right here. All right, there we are. I hit the wrong button, but no problem. So down here, we're building a parabola. We're trying to go down and build a focus curve. At the center of that curve, that's where our perfect focus will be. And you'll see it create it right there on the screen. It makes a line and a curve of best fit, and then it puts the exact focus where it has to be. And right now you can see that it's going to be probably right here somewhere. And it is. There we go. And I let it finish the focusing because it'll either stop early like it did now, or it'll actually go through and do a refinement. Okay. I'm trying to get it to pay attention to my mouse clicks. Why is it not doing it? Okay, well, I'm not getting any response here. Oh, I know why. I'm being stupid. Okay. Now I'll do it. Here we go. Sorry, made a mistake. Alright, so it's going to swing across, and then it's going to come back in and focus perfectly. There we go. Now we're focused. Alright, and out we go. And now we can go in here and do this again. And this time we'll do a 55-second shot. And we have been guiding all along, so we just have to tell it to go right ahead and go. Alright, and we do our live stack now. And this here, the stars are out of focus a little bit, and that's terrible, so Alright, so as you can see, we're doing the countdown over here. And we have 4 seconds left. And now we'll see the image. And it should look better than it did before. And it certainly does. Now, as this gets refined, we'll notice that it will look very nice. Look at all that, and you even have color in there now. That's really pretty. So Thor's helmet now is a showcase object here. So many stars that it's just, it literally is annoying. Ronald asks, why is it green? ERRT radio. It's green because the material that was blown off of this star, which is called a Wolf-Rayet star, that material is actually ionized oxygen, that doubly ionized oxygen. And when it is, when you see it, you will see that it looks a greenish, sort of a greenish glow like this. This is the characteristic look of ionized oxygen. O3, you know, the doubly ionized oxygen. It's literally 55 seconds, almost too much in here. It's almost overblown. Let's see if we can pull this down a little bit. Look at that. That's neat. Let's see if we can get it to do its thing here. Okay. See all the red? Now we have a lot more red in here. Sometimes you have to take a longer exposure in order to see some of the fainter colors.
Izabela asks, where the Wolf-Rayet stars stand in the Hertzsprung-Russell diagram?
Well, the Wolf-Rayet stars are odd-looking stars. Okay, let me. The Hertzsprung-Russell types. Okay, OBAF GKM. Those ended up. There was more than that. It was OBAF GKM RNS. All right, and the RNS stars got migrated to other categories. But these stars here, I think that these guys are going to go. What's happening here? Oh yeah, I think Rascally was trying to show that. I'm not sure where they are in the Hertzsprung-Russell diagram because they're going to be very hot stars. What?
They're off the main sequence, aren't they?
Oh yeah, but they're going to be they're going to be giants, so they're going to be farther up high above the main sequence. But depending on exactly where they fall, their heat, their output, their luminosity, they're in a small cluster, but way up above the main sequence because they are now doing other chemical processes in their cores. In fact, they're not converting hydrogen to helium very much anymore because most of the hydrogen gas has been blown away. Yeah. So you have that hot stellar remnant in the middle. And they're not white dwarfs, they're not neutron stars, but they will be supernovae because they're big giant stars. Keep that in mind. Okay, Wolf-Rayet stars won't ever happen to the sun. Okay, well, the sun will never become a WR star.
For all the stars that we see looking out into space, I mean, there are only, I forget, there's not a lot of Wolf-Rayet stars, are there? They number in the hundreds, perhaps?
Yeah, we don't have we don't really know a whole lot of Wolf-Rayet stars. They're kind of rare. So I think that kind of speaks to our level of knowledge about them. There's various types, you know. All right, this is pretty. Here's some subtle stuff we've never shown before. Never seen this. Never got that. And there's something out there too. What is that? I mean, if you think about it, this region around this Wolf-Rayet star is really messy. It's messy and it's hot. A very, very, very deadly place. No place like, there's no place for home there, I can tell you that. I'm looking up something here.
Me too.
You also have to keep in mind Wolf-Rayet stars do something else. They have emission lines, so they're peculiar stars right from the get-go, because they blow off material and then they ionize it and then it glows, and that gives off an emission line. So you get a bright line spectrum with a Wolf-Rayet star as well. So and where that puts it on the HR diagram, depends on what type of Wolf-Rayet star it is, but they're all clustered. Like I said, they're clustered near each other. They're not all over the place.
There are different types.
Yeah, there are.
The separation of Wolf-Rayet stars from spectral class O stars of a similar temperature depends on the existence of strong emission lines of ionized helium, nitrogen, carbon, and oxygen.
Yep.
But there are a number of stars with intermediate or confusing spectral features.
Yeah, they're look at this. Is nice. The Wolf-Rayet star in this image, I believe, is this guy right here. I have to confirm that, but I believe that our star causing this is right here. I believe that's the guy. I will have to confirm that, though. Wolf-Rayet stars are exceedingly hot. They're not a cool star at all. And they're massive. They're way more massive than our sun. We stacked 10 of these. This is the most detailed Thor's helmet we've ever shot. I will say that. Sam S says, "Is this what Bowman saw in the monolith?" Yeah. I imagine you're right. I think Wolf-Rayet stars are fascinating. We've seen them in the Crescent Nebula. We've seen them in Thor's helmet. We've seen them in other places as well. But again, they're very hot, way more massive than our sun, and destined for supernova. They're that massive, okay? So they make a very strange bedfellow in the universe right now. We don't have any... There's nothing comparable to it, you know? They're as odd as black holes are strange. And we don't know why they expose their inner cores and blow off their outer layers. We don't really know why they do that. But they have extremely powerful stellar winds, and that's part of it, right? And why do they have powerful stellar winds? Anybody's guess. We don't really know. But they have very powerful stellar winds.
Mark, Robin Curtis is having a conversation with Izabela. She can't post links. She doesn't have that power.
What? She's not a... Oh, well, crying out loud.
I was going to say, she's not a moderator.
Yeah, well, that's going to change. Why did she not be a moderator? Robin, I think you were a moderator, but if you don't use it, you lose it. And I don't do that. YouTube does that to you. You can now post links. You're a moderator.
Ta-da.
There you go. Oh, you don't want it?
Well, that's how you post links, Robin. You
want to post links? You want me to take away your moderation? Doesn't mean you have more jobs to do. It just means you can actually post links. That's all. Unless you...
I'm sorry, I was just trying to help.
So she doesn't want it. Robin, don't play games with me. I'll take this back and you'll never get it again. Robin's very helpful on our stream. So I would not take it from her. And now if someone says something you don't like, as Izabela says, you can now zap them. Get rid of them. Okay, 14 stacked here. Thor's helmet's looking pretty good.
Just me, or are the colors different than they used to be?
Well, they're more saturated, I think. That at least because we're doing longer exposure.
Maybe I'm just misremembering.
You know, they were always this greenish color. I'll just throw that out there. Ray, I think it was this star here. If I remember, that it was this guy right here is the star that's causing all the havoc. But I have to go back and look.
So this is probably repeating what I asked at the beginning of the show tonight. This is the supernova candidate. Betelgeuse is a supernova candidate.
Yeah.
Betelgeuse is not a Wolf-Rayet star. What's the difference between the two?
Well, Betelgeuse still has its outer envelope, and it hasn't expelled it in a violent stellar wind. This star has expelled its outer envelope in a violent stellar wind. That's characteristic to Wolf-Rayet stars. That stellar wind is extremely, it's one of the main tenets and main characteristics of a Wolf-Rayet star is that very powerful stellar wind. Betelgeuse stellar wind is not the same, and Betelgeuse, being a supergiant, of course, is much bigger than this star. This star's outer envelope is gone, so it's actually a more compact object, and it's going to actually go supernova someday anyway, because that compact leftover remnant in the center is still fusing elements and will make its way to iron and then finally lose its balance. Overall, the hydrostatic equilibrium will be lost and it'll collapse. But Betelgeuse is very, very large, and it's just a supergiant, but still maintains its envelope.
Okay.
This one's envelope is gone.
That makes more sense now than it did at the beginning of the program.
We're seeing this envelope now in the rest of the helmet here.
Yes. Very good.
Okay, Ray says that I was right. This is the star that's the cause of all these problems. You know, these Wolf-Rayet stars, you try shouting them out, you try rubbing them out, and still they blow off their outer layers. Look at that. This is going to be a real pretty process, let me tell you.
You are right, Izabela. That's a world of difference. Izabela put up a link to one of the older images of the Angel Nebula.
Of the older Angel Nebula?
Yeah.
Okay.
It's like from a year ago.
I have one on a decal that's on my wall over here. Is the one that was from a year ago better than the one we see now?
No, it's an image of the Angel Nebula.
Yeah, but is it better than what we just took?
Tonight?
Yeah.
No, it's not. It's not even close.
Okay, so
Very pale and washed out.
okay, so we've kind of improved our capabilities.
Oh, not kind of, immensely.
Very cool. Hey DK, how you doing? DK0018 is in the house.
Excuse me again, please.
Sure. Cosmic Ray, I added you as a moderator. I did not realize you were not a moderator. You've certainly earned that. What's going on, DK? How you been, man? Good to see you here. Okay, we're at 21 stacked here on Thor's helmet. Thor's helmet is actually a smaller object in the sky, because of its distance from us. But as you can see, all right, let me just go out. This is how big it is in our frame. Okay, and this is 4 full moons across, 3 full moons tall. So this is smaller than the diameter of a full moon, but our system, because it's so nice, we go to 100%. We're still only at 80%, 90%. Right now we're at 100% of our sensor. This is the native size of our sensor that we're seeing right here on this camera. So at 100%, we expect to see perfection without grain, and that's exactly what happens.
What happened?
I was just saying that I'm at 100% on the sensor.
You said something about grain.
Oh yeah, I was saying that we're at 100% on the sensor, and at 100%, we should not expect to see any, artifacts from zooming in, and we don't. If we zoom in more, we will. DK says, I asked him how he's doing. He says, doing well. Working morning shifts. I haven't been able to get on. I miss you guys, though. Yeah, you know what? We miss you, too. We love having you here. Look at this little subtle ribbon right here.
Mm-hmm.
That may reconnect. It may connect with something else. When we process it, we might see.
Maybe per what Cosmic Ray says, seemed like I remember where I mentioned that it looks different in color. I thought I saw more red in the past.
Well, I don't know.
Being a Wolf-Rayet star, it's blown off its hydrogen, hasn't it?
Yes. It's also blown off a hefty amount of oxygen. Now you might say, how come we see a lot of emission nebula that are red, and how come we see a lot of nebulae that are green? And in other words, why is it always hydrogen and oxygen? You know, there's more than that here, but the fact is that you have to understand the abundances in the universe of these elements. Okay, hydrogen is the most abundant element in the entire universe. Okay, next is helium, then carbon, believe it or not, and then guess what's next? Oxygen. So it stands to reason that there'll be a lot of oxygen mixed into a lot of nebulae, and that's what we see.
I know we've talked in the past, looking at planetary nebula, for instance, the dumbbell comes to mind that we see red neon in it sometimes.
Yeah, we do. And that's only because we get a spectrum of a dumbbell, and we know that there's some neon there along with the hydrogen emission. Otherwise, you could easily mistake the red for hydrogen.
Yeah. Well, if you're old enough to remember neon signs,
Yeah.
neon is a notably different shade of red than hydrogen is.
It is, but your sensor has to be adjustable or adjusted and calibrated, right, in the camera. So you may not be able to say, oh, that's neon, that's hydrogen when you look at a nebula, unless you actually have perfectly calibrated systems.
Yeah.
And I dare say that most of these systems, including this one here, are not 100% calibrated. As far as details that may not be showing well, Ray, you have to wait until we process, because we're getting all the raw data here, and sooner or later that raw data is going to translate into a far better image. Okay, like you can see there is this large hydrogen cloud down here. That will show when we process. Right now, though, the raw file and this file doesn't show too well. And I get it. If we want to see what's really here, we hit this one. Okay, and move that over. And back out and check it out. See what's there.
A lot more.
Yeah. A lot more going on there. And the stars are just annoying.
Yeah. But all that star stuff being spread back out into the universe to seed future stars.
Yeah, and probably planets.
And planets.
This is really pretty. Okay, well, we're good here. I'm going to add Thor's helmet in here. It may actually just come right up. I'll have to see. I might have done this before. Okay, did not. Here, that's good. This is number 29 coming in.
Ronald, I don't think so. If you read about Wolf-Rayet stars, though, some of them, rather oddly enough, some Wolf-Rayet stars are thought to be in the centers of some planetary nebulas. You wouldn't call this planetary, would you, Marc?
I would not. I would not.
This is where the classification gets pretty confusing to me. Some planetary nebulas instead of a garden variety white dwarf in the middle, it's a type of a Wolf-Rayet star, which would seem almost diametrically opposed to a white dwarf star. But
well, white dwarfs are very hot, okay, and white dwarfs give off a lot of ultraviolet energy, and white dwarfs can ionize clouds like this out to similar distances. But the problem is that we're talking about a massive stellar wind in the Wolf-Rayet star, and not a lesser wind actually in the white dwarfs. Ray asked the question, so you're not processing now, because I mentioned in processing we'll bring out the other hydrogen. I'm only doing rudimentary processing, Ray. This is the histogram down here. I'm playing with the mid-level, okay, where we can actually bring it in and do this to show what's going on in there, or drop it down to dig into the details hidden in the high dynamic range, right? And we can play with these kinds of things. This is it. I'm not doing actual image processing on this right now. All right, but that once we do, I remove the stars and I operate only on the nebula, right? And then I put the stars back in as a separate layer, so I can just turn them off, turn them on, and then we can actually study the objects just as they are, without stars in them. So I'll get rid of that Wolf-Rayet star and be able to see just the loops, gossamer bubbles that are being blown by this star. And that's kind of important stuff to me, anyway. All right, while we're waiting, let's go here and do another image here. This will be a 20-second image, and we'll check it out in just a minute. Hey, Kathy Prinisek, how are you? She knew Ron had a birthday, yeah. All right, there we go. What's our sky look like now?
I bet Jupiter is gone now. Yep.
It is. We have the Bird Turd Nebula. I'll remove this for now. Come here. Get out of there. There we go.
And you see,
there's Cassiopeia out there, the W, right there.
Yeah, it's getting low in the northwest.
Yeah.
Orion is actually pretty much across the meridian now, too.
Yeah. Yeah, because we're actually out here now. Okay, let's bring that down. Okay, this is 32 stacked. We're going to go to 33 and pause it. And there we are. We're at 33. So now we're going to save this as Thor's helmet, first of the season. And then save it exactly as seen.
Well done.
Yeah, this looks really nice. So we'll be able to process that and see what that looks like a little bit later on. I have to decide if I'm going to go to bed tonight or not, because I might choose to stay up and process.
That's absolutely right, Dean. When you look at that all sky image, the winter circle's up there. All the winter circle is west of the meridian by local midnight now. The last ones being Procyon and Pollux.
Castor and Pollux.
Yeah.
All right. Let's.
And that's the stars of springtime over on the left side of the screen.
Yeah, coming in.
Can we look at Messier 41?
Yes, we can. That's a good idea. All right, so here's what we'll do. We're going to come in here and look at the Messier 41, the little beehive. here. Here we go. Off we go. Zoom. You can see the telescope moving right there. It's ready to go, and here's the little beehive right there.
I always thought this was a pretty star cluster.
It is. And we'll take some pictures of it for you, Daryl. I got a satellite moving across up there. Okay, so let's head east a little bit. All right. That's very pretty.
You don't have to take pictures for my sake. I've seen it many times. It's just nice to look at.
Yeah, but I'm going to,
Well, I'm sure others would enjoy it.
yeah. All right. There it is, centered up nice. Okay.
I saw earlier somebody mentioned chat that I guess William Herschel discovered Thor's helmet too.
Oh, I think that's true.
Yeah. What it must have been like to have been William Herschel, and you know, to be the first to find so many of the.
Yeah, but keep in mind that William Herschel also had to clean the speculum metal on his telescope in order to be able to see anything.
Oh yeah.
And the telescope was weird. It didn't have a conventional eyepiece. He basically stood in the back end and kind of looked at the reflections off that mirror. Very strange system. Alright, we're going to do a 35-second exposure of this. Alright. And we'll call this Little Beehive M41. Yep, I spelled that wrong. I'll spell it right. And first of all, we're going to live stack it now anyway. Clear the last one. No. Clear. And I will change the name. Because I call it Beehive and not Beehive. Okay. So now the next one is going to look like it should. And here it comes. Look at that. And let's actually get it to process. Get rid of this guy. That's too much. Pull that down. There we go. That's beautiful. Beautiful, beautiful.
There's a yellow star in the center.
Yeah, right there. Very nice.
Can you
Hold
go to
on hold on 1 second. I'll go to Solarium in a second. I gotta do close the door. Hold on. Okay. That's pretty.
Mm-hmm.
There's your stellarium.
Very good. Okay, thank you.
Okay. All right, I'll zoom out a little bit. There's a lot going on around here, I'll tell you that. M46 and M47 we should look at too.
Mm-hmm.
Yeah, we will. Okay.
Dean, Marc can shoot me down if I'm wrong, but it's a pretty typical open cluster. They would have all formed together in a nebula, and once the stars came into being, they blew away the nebula, and the open cluster is left, and open clusters tend to slowly come apart over time.
He's absolutely correct, Dean. I mean, he didn't need me to correct anything. Most of the open clusters, when they form, as he mentioned, they form in a stellar nursery. They don't just form out in space, and they form in a stellar nursery, and their copious stellar winds, over the course of millions of years, blow that gas away. So that's what we see, and so that's why they look like they're all alone out in space. But there used to be gas there, and there's studies that map neutral hydrogen in those regions, and you actually see that there's some neutral hydrogen surrounding these stars and stuff. So there's a lot of additional gas there you just don't see right now.
And if can we go back to there we go. You might remember when we looked at the double cluster. Good night, Michael Hedrick.
Mike, thank you. Good night.
Stars and open clusters tend to be similar types of similar ages, so they have the similar color. And it makes me wonder about the yellow stars I see here. We noticed in one of the two clusters in the double cluster at Perseus that it has several notably yellow stars amongst a bunch of more blue stars, blue-white stars.
Yeah, these are there's one here. I mean, some clusters are old, and some clusters will have stars that have achieved, an evolutionary state where they actually have moved to red giant phase.
Yeah. And we found that out with the ones in the double cluster.
Yep.
Sometimes,
right.
Stars like that might be just unrelated foreground stars, but
yes.
Sometimes they are physically related to the other stars in the cluster. They're just sort of some of the earlier ones to have started moving off.
Yeah. You can see there's plenty of them here. Yeah, so there you go. So that gives you an idea. And if you see them here and you look around and you don't see them elsewhere, you can see how maybe there might be associated with this cluster because they're here and they're not elsewhere. That's kind of an interesting thing.
Makes me wonder about the bluish one down at the lower left.
See, to me, that makes me feel like that's a foreground star.
Yeah.
To me, that's what I feel.
Yeah. And then there's another yellow one right next to it, though.
Yeah.
Just
this one
below
you mean?
Yes.
Yeah. Yeah, I didn't circle that one because I didn't have it. Well, you never know. I mean, it could also be that that's the brightest star, and it is in the cluster. Maybe it's in the process of being ejected from the cluster, if it's at the same distance.
Mm.
But that's a beautiful, beautiful, beautiful little cluster.
Thank you for showing it.
Sure. I'm gonna wait for the 12th image to come in, and then we will head on out.
Going to 46 or 47 next, you said?
Yeah, I am.
Mark, do you remember offhand what your latitude is there at the observatory?
We're at 33 degrees north. You can calculate when the comet's coming up.
Yep.
There you go. All right, so what we're looking at is that guy, the little Beehive cluster, spelled wrong. It's okay, spelled right.
Okay, the comet is 14 degrees high here, and I'm at 30. I'm actually just a hair below 39 north.
Okay, so it's still near the horizon for me.
What
Arizona.
did you say it was there?
33.
33. Okay, so 6 degrees difference.
Yeah.
It's 8 degrees above the horizon in Arizona.
Yeah. Hey there, Frank Rutherford. Frankie Rutherford is with us. How you doing? You're in Greensburg, Indiana. That's cool. Thanks for letting us know. I always like to know where people are from. We've been doing this for several years, Frankie. I don't know if you've been following us. Make sure you subscribe. You know, that'd be kind of cool. Subscribe and like and do all those things, you know. Oh, look, speaking of subscribe, there's that thing. Hey, very good. Nice. All right. So I will pull this away because we know what it is. Smear you. Pull the nameplate out. All right, and let's save this. We have 15 stacked here. We're going to do that. Pause. Save. And little Beehive M41 cluster will go up to our database where you can get to it right here. SkyTourLive.com. In probably 30 seconds, this will be available for you to download just like you see it here. Okay. Our server is free, publicly available. And we do have a Patreon now. So the Patreon, Patreon will allow you to get highly processed imagery. That's very, very large, high resolution imagery, full sensor size images for you. And they're fully processed and beautiful. They're suitable for making into a desktop background. They're suitable for putting on canvas and metal and printing. I mean, it's really quite nice. And depending on your Patreon level, if you're a $10 a month, you get four images that we've created in the last month of high res, and they rotate each month to the next four. We do way more than 4 objects though. And if you get a higher level of Patreon, then you actually get the entire suite of images that we highly process for you. So that's pretty cool. All right, so this guy is all set, and we can get rid of this. So this is Mesher 41, a really pretty cluster.
Thank you for doing that.
Yeah, of course. And now we will go to night vision mode and now take our trip over to the next item, which is right there. And this is the guy that is going to be kind of interesting. Has a strange name. It's a Calabash Nebula, or it's a planetary nebula. A very interesting location. and you'll see there's two clusters here. This is M46, and this one over here that just went out of field is M47. Well, we're going to focus on M46 right now, and I'll show you why. Now you can already see why.
I see why.
Yeah, you can already see why, yeah. Now, here we were talking about Wolf-Rayet stars and knowing how they can be confused as planetary nebulae, which are the end state of stars like the sun. The thing is, Wolf-Rayet stars, those stars are massive stars. The stars that create nebulae like this, on the other hand, are a lot lower in solar mass. They're not very much more than the mass of our sun, and they are possibly much less. All right, so we're gonna check this out. We're gonna zoom in on this while we're at 1 second exposure, and there you go. Look at that. That's a really cool object, and that object is a planetary nebula. But this seemingly goes against what we've talked about. Here's a hot young cluster of young stars. But wait a minute. This is the end state of a star. So how could a star that's highly evolved be in a cluster of young hot stars? That's a question for chat. You know? How can this star that's almost it's almost reached the end of its life fully be mixed in with stars that are hot and young? Kathy Prinisic says it's not the same distance. Very good observation, very good thought. Actually, you know, it's rare people get the right answer right away. And Ronald is on the right track as well.
Sorta.
Yeah, kind of. Just the wrong direction. Okay, it's a straight line. It's just the wrong side of the line.
Wrong way, Ronald.
Kathy, I will tell you, thank you very much, Kathy. You got it right. DK, good call, but wrong direction. This object right here is about 2,000 light years away from us. And this cluster is about 4,000 light years away. So we're seeing one of these things where we see this is the planetary nebula, and this is the cluster behind it. So this is a line of sight illusion. Isn't that cool? Rascally Rabbit. And that old star has to keep an eye on them young whippersnappers. That's right, that's right. Want some beans? Very good. All right, let's take a picture of this and get a nice shot of it. Let's do a 20-second shot and see if that's enough to capture this. We've been guiding for a while now.
You sounded like that annoying old 49er robot in the movie The Black Hole.
Oh gosh, remember that?
Unfortunately, yes.
Come on, it wasn't that bad. Hey boy, why don't you come over here? Yeah, look at that. All right, so let's just process this a little bit, and let's make sure the color is matched. And I'm gonna clear that because I wasn't quite ready apparently.
Disney couldn't help themselves. I mean, they had to corn it up.
Well, yeah, I mean, isn't that what Disney does? So this curve is our data, okay? And so this is the bar that says where on the slope of the level, the black level, we go. So we come up here and you see that it gets very, very dark. We pull back and we can actually see that it gets brighter, okay? So we go about 3/4 of the way up the slope. That's kind of where we hit. And then we can take this guy, all right? And let's just come out here a little more. All right, that's too much more. All right, and from here, we can slide this down and start to see details. in this. See that? And as before, you'll notice, just like you saw with other nebulae and even with Thor's helmet, you saw that there was an oxygen component in Thor's helmet. Well, there's an oxygen component here too, right? And this oxygen component is the shell that's being sloughed off, because the way this sloughing off occurred is different from how Thor's helmet was created. You notice how regular this is? It's sort of neat and orderly. Thor's helmet is like, bleh, 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 right? Well, the ejections from the stellar ejections of this gas from the star with Thor's helmet were violent and were subject to massive stellar winds. This is a slow motion process. Okay? What ends up happening is the hot core, which is this bright dot right there, that hot core, which in this case right now is a white dwarf. Okay? It's the contracted core of degenerate matter. No more fusion going on, but very, very hot. All right? It's a carbon and oxygen nuclei on the surface of this dwarf. All right? And that's it's a carbon oxygen dwarf. All right? Sort of like the sun. And then this layer here, you'll see this hole in the middle here. The actual core gets separated from the envelope, which is expanding outward away from the star. But it's in slow motion. Wolf-Rayet stars do that in fast motion, right? So we don't see that here. But you can see why there's confusion with Wolf-Rayet stars, because the same sort of thing happens, but it happens at a very much lower rate for these stars and a much more prodigious rate with these Wolf-Rayet stars. But this is a beautiful little planetary nebula in the cluster Messier 46. All right. And just so there's no confusion, this is what it is. Let me just put that out there for you right there. M46 with planetary nebula in the foreground. So it's an open cluster, Messier 46, with this planetary nebula. And if we back out now, Rascally says, so this star is actually pulling apart. Well, the outer envelope is actually, here's how it works. Okay, when the star becomes a red giant, most stars will become red giants twice. All right, when they become a red giant first, they then they will then contract and maybe start to fuse helium, and they go down something called the horizontal branch, and they start to get a little bit more blue, and then that runs out and they start to contract again, and their outer layers expand again, and they go up something called the AGB branch, or the asymptotic giant branch, and they become a red giant again. When that happens, several things happen. There are thermal pulses which occur where the outer layers of the star just start to push off. Now at this point the star is huge. The outer layers of the star can be so far away from the star that it's not even hot enough to make them into plasma, and you can actually find, like my face right now, okay, let me get in there, we are, okay, and the outer layers can be cool enough to allow molecules to form, and that means that those outer layers will be so far from the star that if you put it where the sun was, we're talking maybe out by Mars. Okay, is where the outer layers of the star would be, and a big sphere the size of Mars. Okay, and so as the contracting core begins to contract more, it causes this stellar wind to push those outer layers away, and we get that separation like we see here. Okay, and that exposes the core as the central part of this, and the outer layers just slough off very slowly, no longer gravitationally bound, because the strong stellar wind from these white dwarfs is pushing that gas and dust that might be there away.
Yeah. Slough is a good choice of word.
Yeah.
It's not like it explodes like a supernova. It just kind of puffs off its outer layers.
Yeah, and we say puffs when Daryl says puffs. Specifically, those are thermal pulses, and the thermal pulses can occur on average like once every 10,000 years. A thermal pulse occurs where the outer layers of the star will move out some more layers will start, and many times you'll see concentric shells around a planetary nebula like this. Again, so named because in the telescope they might look like small planets. So that's what we see here. And you can see the outer layers here have a hydrogen component. The inner layers have oxygen. And certainly we get in there and we'll see a lot more in there with the spectrum. By the way, our first telescope that we had out here, I'm going to use it out here in the East Coast, but we're converting it to use a spectrometer. So means we're going to be able to look at things like this and say, what is in this? We'll catch the oxygen spectrum. We'll see the hydrogen spectrum, and we'll see the emission lines of these different elements, and we'll also be able to look at absorption lines in stars and see how the stars are made. And that's going to be the Connecticut Observatory's main thrust when we get that back up and running. And the two other observatories we have, well, we're going to have, the one we have now, this one, will always be a visual wide field system. And the next one to follow will be a higher focal length, more magnified system. And we're looking forward to that. And that'll be in a few months. But we're getting things together now for it, and it's looking good. So there we go. That's this guy, and there's 23 stacked here. We'll go to 24. It has 24 20-second shots. And we'll say pause. And I'm going to change the name up here. M46. Open cluster, OC, and PN, Planetary Nebula. Alright, so we'll save that. Save it exactly as seen. Okay. Now before we're done, I'm going to go back and I'm going to take a 10-second shot. Alright? We'll just go right into it. But we're going to clear. So the 10-second shot is going to help with the detail in that nebula, let's hope. There we go. So I wanted to show some of the detail in this nebula, and to show it, we need to do a slightly less of a exposure. All right, so this is gonna come down.
John.
Okay.
If we could zoom in on this, it would probably look like, maybe like a cross between the dumbbell and the ring.
Yeah.
And you can just make out, I think Marc pointed out a minute ago, out toward the outer edges, there's a little bit of reddish showing up.
Yep.
Rather reminiscent of the dumbbell.
Yeah, right there. You see some red. Right here, you see some red.
Yep.
Yep. So I did this lesser exposure because if you notice, there's also some spikes that stick off. See those? There's some detail around the outside edges that is actually pretty interesting.
Mm.
So when we process this, we'll use this lesser shot and use this to actually pull out the detail in the middle while actually exploring the cluster with the rest of the exposure. Sean Farber is in the house. How you doing, Sean? All right, so that's pretty cool.
Sam, Is that cloud expanding in all directions or just toward us? It's not expanding really energetically. What's often seen with planetary nebulas is there may be more farther out that the energy of the white dwarf in the middle isn't quite reaching anymore. It's gone beyond. The energy level has dropped a distance from the star set. It's not actively causing emission in the outer shells anymore.
Yeah.
And those tend to drop off at a certain size, a few light years or something like that, I think.
All right, so let's go here and see if I can increase some of the detail in this. So you can see some of the modeling in here now. See that?
I was looking at the image that Ray posted. Actually, that is a nice planetary.
Yeah, it is.
Another one that needs some focal length to really get into.
Yeah. Very cool. Okay, well, this is 22 of these stacks, so we're going to stop here. And we're going to save the same name, so we'll just have two of the same, but lesser exposures. All right. Save exactly the scene. Not bad. Wow. Well, this is quite a night, huh?
Mm-hmm.
Here we go. And we'll get out of this. Go back into our 1 second. Alrighty, and give us this. Take away that. There we go. And let's see if there's just one more that we can look at. Would you guys like to see the Horsehead Nebula again?
Sure.
All right. Or how about the Christmas tree cluster?
Sure.
And yeah, why don't we do that?
Right.
That's better. All right. So that's over here. Because this is literally a stunning location in space. It is a stunning region. So we're gonna visit the Christmas tree cluster. Hey, thanks, Sean. Thank you for that contribution.
Said he's in the hospital.
What? What's the matter?
Broken bones.
Oh man, what'd you do, brother?
Said he lost
What happened,
a fight
man?
with a can of tuna.
What?
Whatever that means. Robin says there's a dark something we're supposed to look at.
Well, did I forget something, Robin? Hold on a second. Let's go back here. Okay, this is another nebula, which is actually really pretty. It borders this. This makes a beautiful, this makes a gorgeous mosaic. So we're gonna do this one too. You can see the dark nebula here. So I'll show it to you. All right, there we go. All right, we'll let this lock in. Then we'll move west, or east rather. right. All right, so let's do 45 seconds here. And kick this out. Head into our stack. Okay. And here we go. No. Okay, and there we have. There is a vast nebula here, as you can see. Yep.
Yep.
Ray, what's your comment about APOD there? I'm not sure what you mean by that. Okay, we're not high enough. We gotta get down lower.
You put up an APOD of the planetary nebula in M46.
Okay.
Which was a very
Right.
nice picture. It is
Okay.
it is a close up of the planetary, and it has a ton of detail in it.
Okay. Well, we get focal length. We can do that too. All right, so let's do this. All right, and now I can move us down a little bit here. This nebula is just stunning.
What, did we divert from the Christmas tree?
We're actually just west of it. We're just west of it. See, this is the major. We're gonna shift left, as you'll see. I'm going longer than I normally might. Okay, this will be a 50-second exposure. All right, and then once we start guiding, it takes 14 seconds to get our guide star. All right, now we'll try it. And we'll clear this. Right now we're actually we're gonna be this has been brought up more into the view. It's a beautiful reflection nebula with lots of dark nebula tendrils. The dark nebula is also that reflection nebula, but it just happens that that reflection nebula dust is scattering the starlight from the star, so you can see it more visibly. 4 seconds. Look at that. Wow. See that? That's beautiful. And this stuff here is the beginning of the Christmas tree cluster and nebula. But look at this beautiful tendril, and this is just stunning. I will color correct. All right, and let's do this correction as well. Move this out and move this in. And then pull this in. All right. Now we're going to be right about there. Look at that. This is a combo platter of hydrogen emission and dust scattering processes all happening. There we go. And where we are is just to the right of the Christmas tree cluster here. All right. So we are here. This is Dreyer's Nebula that we're looking in now. But it's also NGC 2247, right? Also known as Lynn's Bright Nebula 901. And just to its left is this beautiful object that we'll see next. So this is Dreyer's Nebula. Let's call it what it is here. NGC. Oops, screwed it up. Oh, we're gonna get a satellite in here. What a surprise. NGC. Let me go back to that. Back. All right. Uh, 2247. Okay, 2247. It's a dark nebula space reflection nebula, DNRN. Yeah. Sadly, we're going to get a satellite in here as well. And then over here, we will get to the Christmas tree nebula. This is the beginning of the Foxfur Nebula over here.
You got a satellite in there too.
I do.
And if you move to the Christmas tree, that satellite's are going to move over into it.
Yeah.
The one on the right.
I know what you mean. Yeah, yeah. Let's color correct and get rid of some of that color. There we go. That's looking nice. This is just beautiful, beautiful, beautiful. Look at the crescent of Dark Nebula. Yes, there is one right here. And this is going to show up even better here, just in a little bit here. Actually, I can show that now, I think. Let's pull this back a little. And to see what's really here, we can just do a blast on it right now. And you can see there's a lot of material in here that's going to show. Then we got this little beautiful curly Q. Very nice. All right, let's slide this down for a minute. You can see how beautiful and subtle that blue reflection nebula is, huh?
Yes.
And that's how it all looks when we're done processing it. Because we actually can remove all the noise from the image. And removing noise is a very important aspect of it. I can even get rid of the satellite images too, by the way.
You better.
I will. Notice how the dark nebula is starting to show variations in brightness and darkness?
Yes.
That's something that the longer exposure does for us.
I was thinking the one up toward the top right, it's not almost being silhouetted by the star above it.
This guy?
Yeah.
Yeah. I think it is. I think it is.
And there's more pieces over to the left.
Yeah. Let's try zooming in. See what we get.
I asked recently, I think, I mean, we're in Monticeros here.
Yes.
If this is like related to the material around the rosette. The rosette's just to the right or the upper right of here, isn't it?
Yeah, actually it's below it, I think.
Oh. But still,
So the rosette, I think, is down below here. There it is.
okay.
But you're suggesting that maybe the material of which the rosette is part of could be stretched this far. It certainly could.
Yeah.
No reason why that can't be true.
What I was wondering the other night was if, like, the molecular clouds around the rosette were related to the Orion cloud. And turned out the rosette was much farther away than Orion.
Yes. Yeah.
So maybe this would follow also that it's separate, much farther away.
Really pretty. See, by stacking like this, you know, again, like I said, the dark dust lanes, all this subtle detail is lost with the noise in the first couple frames. But then it rises to the top and that data stays. That data doesn't go away. The noise changes every shot. So as long as that data is staying the same, it's going to overlay and overlay and overlay and overlay, and eventually it's going to climb to the top and be the brightest thing you see in that particular pixel. It's just data. And that's why this is starting to look so much more well-defined. That's why this is starting to look well-defined. That's why this is starting to show detail within it.
Yeah.
Because that's the process that's taking place.
Hello, James.
Hey, this James Dugan from down under. Nice to see you, James. Good to have you. Yeah, see, these are starting to smooth out now. Starting to look more pronounced. Looks really good. What?
Oh, well. Jaws 2 is on the tube.
Jaws 2.
Yeah.
Okay.
That's the one where the shark gets it from biting the high power line.
You told everybody how it ends.
The teenagers are out there right now, and Roy Scheider's trying to save them. Well, they got away from him.
All right.
Tonight's Jaws night on BBC. The first one's good. The second one's stupid. The third one is really stupid, but it has Leah Thompson running around in a bikini a lot, so it's okay.
Okay, we got 13 here. We'll go to 14, and we'll hang it with that. There it is. Just a few seconds, and now we're gonna pause it and save this. This will be NGC 2247, and save exactly as seen. Okay. Now we're going to clear and move over. Now all I have to do is, well, first thing I'll do is just zoom out a little bit. All right. Now I'll just move over, head east. There it is.
There it is. Just a hint, folks, the Christmas tree is upside down.
It is, yeah.
Bright stars at the base of the tree.
All right, so now we're gonna drop down a little more because there's another little guy we want to capture as well.
The cone?
No, that's already in there. It's right here. This guy.
Hubble's Variable Nebula, okay.
You got it.
That would have been next on the list.
All right, so all right, here we are. Now, this region is by far one of the more active regions. It's next to the Horsehead region. This one looks to me like a much or very similar region. There's Dark Nebula, there's Diffuse Nebula, all throughout this whole region. And now that we're here, let's do a 45-second shot here. Oh, Kathy, sorry, man. I know it's 1:45, and I'm doing another shot right now. I probably shouldn't be.
Yeah. I can hear the pumpkin coming. I think I'm going to have to call it after this.
All right. What's going on here? Oh, it's about time.
That'll teach that stupid shark.
Right.
Fish and chips for dinner.
What?
Good night, Kathy.
Thank you for coming, Kathy. It was good to see you. Okay. Oh, look at that.
Nice.
Yeah, this is beautiful. And there's Hubble's Variable Nebula down there. Just beautiful. This is, again, 50 seconds, so, or 45 seconds. So, longer than we've taken exposures up here, actually. We've not taken any exposures this long. And I think if we play our cards right, we won't see that other satellite coming in yet.
Jan,
Yeah.
stop that.
Well, if you feel the need to call it out, then serves you right if you yawn.
You're making me yawn is what you're doing.
Hey, Poison Arrow Frog, what's going on? No, we're not using the Raza. This actually, you can see the system right there. It's actually an F8 10-inch that's been converted to F2. So we're actually using this system. It performs sort of like a Raza, and we get 25 times the speed photographically. You know, I mean, 45 seconds and we get all of this without any problem. So how you doing there, Poison Arrow? It's nice to see you. Oh, it's very fast. You're absolutely right. Very fast. Hey, if you haven't subscribed to us, join, man, because we do this. We have several hundred streams up on there now. You know. Dean Bustador, I already missed Christmas. And now you're imaging a Christmas tree. Yeah. Notice here, this is the Phosphor Nebula right here. And it shows beautifully here. And let's zoom in on the cone, which is this segment right here. This is the Cone Nebula. It's a dark nebula. There's the first pillar, then the second pillar. Okay, then there's several more down here. These are areas that are being eroded by the hot stars and maybe by the stars up above here, in fact. In the Christmas tree cluster. These stars could be eroding the gas and dust around here. And this area might be preserved because it's denser, and so the erosion can't take place on the back side of it as easily. So that we always get what we call them stalks, or elephant's trunks, actually, which is really what we're looking at here, essentially. Let me just darken this up a little bit. Look at that. That's just beautiful.
Can you bring
Not
the
bad.
top, bring the top down just a little bit? There you go. If you extend the walls of the cone, you know, the lines, the angle, the taper of the cone, it's like it's pointing at the real bright star there at the top.
Yeah, pretty close.
Basic Christmas tree.
Yeah.
You know what might be causing the shape of the taper.
Yeah. Well, I'll show you the overall view here. That's just a gorgeous region. There you go.
Comet is 13 degrees high in Arizona.
Okay. Too low for us still.
Still too low.
Yeah, it has to be at least 35 degrees or so, 33 degrees. Maybe 31. Hey, Poison Arrow Frog, man, thank you for subscribing. I'm glad you were alerted. Now, when we talk about the different features in this region, just want to make it clear what they are. This is the cluster right here. Okay. This is the cone right here. It looks like a cone, right? And when we talk about the Phosphor Nebula, we're talking about this beautiful, subtle material right here. This stuff is really cool. Okay, you can see it on this side too, coming down here. Right there. So that's the Phosphor Nebula. Now the really cool thing is Hubble's Variable Nebula. This right here. This little guy, let me make sure you can see it now. Pull this out of the way. So now, Hubble's Variable Nebula, right now it's really overexposed, but if I remove some of the brightness, I might be able to show it to you. Let me do that. Pull this way down. It still might be a little too overexposed, but let's just go down and check it out. NGC 2175. Yeah, that'll be another time though, Poison Arrow, because this is gonna be our last object. It is actually, it's almost 2 a.m. here in Connecticut. I am running this out in Arizona, but okay, there is Hubble's Variable Nebula. Look at the detail on that. That is really pretty. And let's see if I can pull off even more brightness out of that. Wow. That's nice. You can see the subtle difference. Now, if we were exposing for a shorter period of time, then you would see this a little more detail down there. All right, so let's get it back. Hey there, M. Turner. Are you talking about the comet? Because if you're talking about the comet, it's not high enough in Arizona right now, but it will be. I mean, it's January 22nd. By the 30th, it'll be high enough for us to see. It's moving very fast. Okay.
Mark?
Yep.
How about just one more?
Uh-oh.
Do NGC 2175.
Well, he requested it.
Yeah. It's open cluster in Orion, embedded in a diffuse nebula. A really wild looking picture of it.
All right. Well, we'll do one more.
Okay.
I'm going to go to 14 on this, and we'll stop. I'm all for it. That's cool. All right. Needless to say, that's pretty cool. So what we'll do is we're going to say Christmas tree cluster.
M. Turner, the comet is going to get higher and higher night by night. Give it another 3 or 4 nights and we might be able to take a look at it.
Yep.
Certainly by the end of January, 1st of February, it's going to be much higher even than the North Star. It's going to be about 50 degrees up in the sky. And,
that's right.
Earlier in the evening too. It should be easier to see then.
Alrighty. Let's go to our planetarium program and let's do 2175. Alright, Poison Arrow, I guess you win tonight and I'm happy to oblige, so that's cool. We'll do it.
I think you'll be glad you did.
Alright, didn't I do this before? This sounds familiar. Sounds familiar. Uh-oh. That's what I thought. Okay. That's the Monkey Head Nebula.
Oh, okay. No wonder.
Yeah. I knew it sounded familiar. It's way over there, but we can give it a shot. I thought it was something I knew.
Sorry,
Sounded very familiar.
Since we're here.
No, it's okay. Yeah, there it is. Okay, so what I'll do is I will bring it up into the field here. Actually, I haven't done any 45-second shots of it, you know, so this will be kind of cool. All right. So we'll give it a little zoom into it ahead of time here.
The picture looks different. And the article never mentions the monkey head. They just say NGC 2175.
Yep.
I should have known.
That's all right. I sort of did know, but I couldn't think it through. It is almost straight up, so this might be one of the better shots we ever took of it. So let's do this. 45 seconds, and off we go. But remember that Christmas tree location. This was beautiful, wasn't it?
It is. That's very nice.
That's a really, really pretty scene. You know, and we can actually do a lot with this image. Yeah, for sure.
No, I wonder when I look at that. Like I said, if you see the taper of the cone, it's like that taper is being defined by the distance of
yeah,
a bright star.
yeah. There we go.
Narrative. And if I remember right, yeah, we can see the monkey's head right now. And as you build a deeper exposure, it's going to get harder and harder to see the monkey head. You can see his mouth, you can see his nose, you can see his eyeball, see his ear. Looks like a fire monkey.
Yeah. And Poison Arrow, once this is saved, it will be out there for you to pick up for free. It's going to be on our server. So you can go grab it when it's done. It'll be up there in about 30 seconds after we actually save it, all right? So we'll keep going now. I want to show you while we're here, the monkey head has some really interesting characteristics. You'll notice that we have these dark filaments in here as well. And the stars in here are kind of carving out a cavity in here with their stellar winds. All young stars have stellar winds. Not bad. I like this region right here. Let me show you. Look at this right here. See that? That's cool. I don't know what's causing it. I mean, I see there's some kind of reflection nebula in here. You know? Poison arrow, yeah, it's a good argument for hyperstar. I mean, it's 4 full moons across, 3 full moons tall. So we can't look at planets, for instance, but our next system, we have another telescope here that's going back in the dome, or going back in a building. Once we build the building in the spring, we had to. I sold it because we basically outgrew it. Right, that computer, that telescoping computer for it is back behind me here in my bunker here, and we have a third observatory going in Arizona. This telescope is in Arizona, 2,500 miles from me, and I'm running it from here in Connecticut, and then. All the images we do come out of the observatory, go shipped up to the cloud where they're dropped in a public server that I created for everybody to get to and grab stuff for nothing. It's very good. It's a really nice system. Allows us to offer you a tremendous variety of incredible imagery. Petita PG, how are you?
Poison arrow frog, I dropped that link up above you. That's where this image will land on the server. You can access it there.
And you can also, if you don't know where to go, right here under me here, SkyTourLive.com. Okay, SkyTourLive.com is our portal, and it takes you to this stream on YouTube. It takes you to that Patreon. It takes you to our gallery of some of the coolest shots we've done. It takes you to a story of who we are and how we came to be. And it also can take you to the database. You scroll down just one section and it says, hey, take me to some great pictures. And there's instructions in that little list to show you exactly what to do when you get there. All right. So it's just it's a raw drive, and you can go zipping through it and check things out and download them for yourself. So it's all available to you, and we're happy to do it because we're nuts. I mean, who else would stay up half the night to show you stuff like this? Put this here. Okay. So NGC 2175's got a pretty beautiful visage to me. It just looks pretty.
Yeah.
Okay. Well, we'll let this 9th one stack and then we'll call it.
Yeah. I am turning into a pumpkin now.
Well, don't fall on the ground. You'll be squashed.
Uh-huh.
Okay, so monkey head there. NGC 2175. Save. Okay, so now that's the raw file, the FITS file. If you have Photoshop and you want to bring it in with a FITS reader, there's one out there you can get. Or if you just want a pretty picture, then save exactly as you see it. That's what you got here. Okay, I do that as well. And that, this is an example of what you get. So, here's the monkey head. That's the actual image that we just took. Okay, and that'll be on the server just like that in probably 15, 20 seconds, maybe 30 seconds. You know? So, that's good. And we are done for the evening. I hope you guys have enjoyed this as much as I've enjoyed doing it for you with Daryl. You know, we enjoy it. Daryl's in Colorado. I'm in Connecticut. The telescope is in Arizona. Hey, man, we're crazy that way. So.
Thanks for coming, everybody. It's been fun.
Yeah. Love having you guys. So we'll talk to you again. And remember, when you go outside, keep looking up. You never know what you'll find. Alright? So we'll see you in the next stream. Alright? Adios, amigos. Good night, everybody.
Good night, all.